You are already comfortable. That is the most important part. The day has done all its work, and now there is nothing left that needs your attention. The light is low, or maybe it is completely dark, and the quiet around you is not an empty quiet. It is a full quiet, a soft quiet, that has room in it for one slow voice to wander through some gentle ideas. Nothing here will ask anything of you. Nothing here will try to be loud or surprising. We are just going to walk together, very slowly, through a few ordinary things that most people never stop to think about. And even the walking is only a way of saying we are going to let our minds drift a little, like a leaf on very still water, turning only because the water itself is turning underneath. Think about the last time you crossed a bridge. Maybe it was a small one, a short concrete span over a creek you barely noticed. Or maybe it was a long one, the kind that hums under car tires and stretches out across a wide river or a bay. You probably did not think about the bridge at all while you were on it. You were thinking about where you were going, or what you would do when you got there, or you were not thinking about very much. The bridge was just there, doing its job so quietly that it disappeared. That is what good engineering does. It disappears. It makes itself so ordinary, so reliable, so much a part of the background of daily life, that you never have to wonder whether the road will hold you, whether the building will stay standing, whether the elevator will lift you safely up to your floor. The cleverness is hidden not because someone wanted to hide it, but because it works so smoothly that there is nothing to notice. This is the quiet thread that will run through everything we talk about in these hours together. Behind the most ordinary things, the things you walk on and ride in and look past every day, there are simple, calm ideas holding everything in place. Ideas about balance and give and take, and forces that push and pull. None of it is complicated in the way that might make your mind work hard to follow. It is complicated only in the sense that a river is complicated, full of small motions that add up to one smooth flow. You do not need to trace every small motion. You can just watch the surface, or close your eyes and feel the current carry you. So this is not a lesson, not in the way you might remember from a classroom. There will be no test. There is nothing you need to memorize or hold on to. If a thought slips away before the sentence finishes, that is perfectly all right. The words are here to keep you company, not to demand your focus. Think of them like raindrops on a window, one after another, each one making its own small path down the glass. You do not need to follow any single drop all the way to the bottom. You can just let the whole pattern move in the corner of your attention, a quiet something happening while you rest. Tonight, and in the nights that follow, we are going to look at a handful of everyday marvels. A bridge with its long, sweeping cables, an airplane wing with its tip turned up like the curled end of a leaf, a tall building that sways just a little in the wind on purpose, an elevator that lifts you without straining, a road that is not quite flat, though it looks flat to the eye, a dam that holds back a whole lake with nothing but its own weight and its own shape, a round window in the side of an airplane, the gears on a bicycle, a manhole cover in the street, the springs under a car seat. Each one of these things is something you have seen, maybe hundreds of times, maybe without ever really seeing it at all. And each one holds a small, quiet secret about how the physical world works, a secret that engineers learned slowly over many years, sometimes by getting things wrong before they got them right. But we will not rush toward any of those secrets. There is no hurry. The night is long, and the only goal is to let your mind settle, to give it something calm to rest on, that is not the thoughts of the day. Sometimes the hardest thing about falling asleep is the feeling that your mind is still spinning, still sorting through everything that happened, or everything that might happen tomorrow. A slow story about bridges and gears and round windows gives that spinning mind a different kind of track to run on. One that does not loop back to worry or planning. It just goes forward, one step at a time, and eventually the steps get softer and farther apart, until you do not notice when they stop. We will begin with bridges, because a bridge is a good place to begin. A bridge is a simple idea made real with enormous care. You want to get from one side of something to the other. The something might be water or a deep valley or another road. The bridge is the answer, a path hung in the air where no path could naturally be. But the air does not hold things up on its own, so the bridge has to hold itself up, and hold up everything that crosses it, using only the materials it is made from and the shape those materials are arranged into. That is the whole puzzle of engineering in one image, making something stand where nothing stood before, using the rules of the physical world rather than fighting against them. The very first thing we will look at, after this gentle opening, is something so small on a bridge that you might never have noticed it, even if you have driven over it 1,000 times. The gaps, the little metal teeth, like a zipper laid flat, that you sometimes feel as a slight bump through the car tires when you enter or leave a bridge. Those gaps are not a mistake. They are not a place where the bridge is coming apart. They are a place where the bridge is breathing. That is the image to hold on to. A bridge breathes. It expands and contracts. Just barely. Just enough that if you did not give it room to move, it would tear itself apart from its own quiet effort to exist in a world that gets hot and cold. We will spend a long, slow time with that idea, because it is the first and simplest example of a rule that shows up again and again in the things people build. You have to leave room for movement. Rigid things break. Things that can flex and shift and breathe, even in the smallest ways, they last. After the breathing bridges, we will lift our eyes up to the sky and think about airplanes. Not the whole airplane, just the very tips of the wings, where the metal curves upward like a small fin. That little curve has a job. It is calming the air. When a wing moves through the sky, it stirs the air up, leaves a kind of invisible swirl behind it. That swirl is wasted energy, energy the engines had to spend. The upturned tip, which is called a winglet, is a way of gently smoothing that swirl, telling the air to settle down, to not waste so much of the plane's effort. It is a quiet kind of politeness to the sky, and it saves fuel, which means it saves money, which is why you see those curved tips on so many wings now. But the reason it works is not about money. It is about flow, about letting a force move naturally, rather than trying to stop it harshly. From the sky we will come back down to the ground and stand in front of a very large bridge, the kind with tall towers and thick cables that droop in a long, graceful curve between them. The Golden Gate Bridge, or one like it. And we will ask the simplest question: why does it not fall down? The answer will introduce us to two words that sound like opposites, and in a way they are: tension and compression, pulling and pushing. The cables are being pulled, stretched tight along their whole length. The towers are being pushed, squeezed down into their foundations. The bridge takes the downward weight of the cars and the roadway and turns it into a pulling force in the cables and a pushing force in the towers. It is a conversation between pull and push, and as long as the conversation stays in balance, the bridge stays up. We will spend a calm, careful while with tension and compression, because once you see them, you start to see them everywhere. In a rope, in a chair leg, in the bones of a building, in your own spine when you sit up straight, and then let yourself relax back into the pillow. After the bridge, we will look up again, this time at buildings so tall they seem to touch the clouds, skyscrapers, and we will ask why they are built to sway. It sounds wrong at first, that you would want something so huge and heavy to move in the wind. But the alternative is worse. A building that tries to stand perfectly still against a strong wind is a building that is fighting the wind with all its strength, and eventually the wind will find the weakest part of that strength and snap it. A building that sways a little is a building that is saying to the wind, "All right, I will move with you, just a bit, and then I will come back." That give in the system saves it. And inside some of these swaying buildings there is an even stranger thing, a huge weight, a ball of steel or concrete, hanging near the top, that swings in the opposite direction of the sway, like a dancer moving counter to their partner. This is a tuned mass damper, and its whole job is to be heavy and to move at just the right moment to calm the building down. It is a lullaby made of steel. From those great heights, we will step into something much smaller and closer, an elevator, the little room that carries you up and down inside a building. And we will wonder how a motor that is not nearly as huge as the building itself can lift a box full of people, floor after floor, without burning out. The answer is a counterweight, a heavy block that rides up and down on the other side of the cables, balancing out most of the weight of the elevator car. The motor only has to deal with the difference, not the whole load. It is like a seesaw where one side is almost as heavy as the other, so a child can push it with one finger. Balance again. Balance doing the heavy lifting, so the motor can rest easy. Then we will come back down to the ground, literally, and look at the road under your feet or under your car. A road looks flat, but it is not flat. It has a gentle curve, a slight rise in the middle, and a slight fall toward the edges. This curve is so subtle you would never see it just by looking, but it is there, and it is the reason water runs off the road instead of pooling in the middle. Pooled water is dangerous. It can make a car skim across the surface, losing touch with the pavement. That gentle curve is called a camber, or a crown, and it is another one of those hidden shapes, doing its work so quietly you never have to think about it. But tonight, we will think about it, just long enough to appreciate it, and then let the thought go. After the road, we will turn to something immense and solid, a dam, a wall of concrete holding back a whole lake. The water wants to push the dam over, or slide it downstream, or seep through it. The dam resists, not with any motor or moving part, but with its own enormous weight and its own clever shape. A gravity dam just sits there, so heavy that the water cannot budge it. An arch dam curves into the water, so the pressure of the lake pushes the dam tighter into the canyon walls instead of pushing it over. It is a kind of quiet judo, using the water's own force to lock the structure in place. We will stand, in our minds, at the base of the Hoover Dam, feeling the cool air rise off the concrete, and think about what it means for something to hold back so much weight just by being heavy and being curved. From that great wall of concrete, we will move to something small and round. An airplane window. Have you ever noticed that airplane windows are not square? They are round, or oval, with no sharp corners. There is a reason for that, and the reason comes from a sad story in the early days of jet travel, when engineers were still learning about how metal gets tired. Metal fatigue, that is the phrase. Metal, when it is stressed over and over and over, even by forces smaller than what would break it once, can begin to crack, and cracks like to start at sharp corners. A square window has 4 sharp corners, 4 places for stress to concentrate. A round window has none. The stress flows around the curve like water around a smooth stone. The engineers learned this, and they changed the design, and now every airplane window you look through is round. We will tell that story gently, without drama, because it is not a story about disaster. It is a story about learning, about paying attention to the quiet signals the material gives before it fails. Then we will get our hands a little dirty, in our minds, with gears. Gears are just wheels with teeth, but the way they work together is a kind of magic made ordinary. A small gear turning a big one gives you more force but less speed. A big gear turning a small one gives you more speed but less force. That trade is called mechanical advantage, and it is not a cheat. You are not getting something for nothing. You are trading one thing for another, the way you might trade speed for strength when you shift to a lower gear on a bicycle going up a hill. Your legs spin faster, but the pedals push harder. That is the trade. That is the quiet bargain at the heart of every machine with gears in it. After gears, we will look down at our feet, at something so common it is almost invisible. A manhole cover. Round, heavy, set into the street. Why round? The answer is so simple and so perfect that it feels like a little puzzle solved. A round cover cannot fall through its own hole, no matter how you turn it. A square cover, if you tilt it just right, can slip through the diagonal and drop into the darkness below. A round cover also rolls, which makes it easier to move, and it fits in any rotation, so the worker putting it back does not have to line up corners. It is a small, quiet piece of cleverness, hiding under car tires and bicycle wheels, doing its job without thanks. And then, near the end of our time together, we will settle into something you can feel directly. The seat of a car, or a chair, or your own bed. The way a car smooths out a bumpy road. Under the car, there are springs that squish and stretch to soak up the jolts. But a spring alone would just keep bouncing, up and down, long after the bump was gone. So there is also a damper, a shock absorber, that calms the bouncing down. It uses fluid, pushed through small holes to turn the bouncing energy into a little bit of warmth and slow the motion to a stop. The spring catches the bump, the damper catches the bounce. Together they let the wheel dance over the rough road while you stay nearly still. It is another duet, like the bridge cables and towers, like the swaying building and its swinging weight. And finally, when we have walked through all these things, we will let them settle around you like a blanket. We will not test you on them. We will not even summarize them in a way that asks you to remember. We will just let their images drift back through, one or two at a time, softly, the way you might watch the last few snowflakes fall after a long, quiet snow. The swaying building, still now in the night air, the round manhole cover, resting in its rim, the curved road, dry and quiet under the streetlights. These are the things that hold our world together, and they do it so gently that we can forget they are there. That forgetting is a kind of trust. And that trust is what lets you close your eyes and let go. So this is where we begin, not with a bang or a bright flash of interest, but with a slow settling in. You do not need to be anywhere else. You do not need to fix anything, solve anything, or even understand anything completely. The words will keep coming, slow and steady, and you can let them wash over you like warm water, taking whatever shape your resting mind wants to give them. The first thing we will look at, when you are ready, is that small gap in the bridge, the one that lets the bridge breathe. But we do not need to go there yet. For now, just breathe yourself. Feel the weight of your body resting on the bed or the couch or wherever you have found your comfort. Feel how the surface under you holds you up without any effort on your part. It is doing its quiet work, just like the bridge, just like the road, just like all the other ordinary marvels we will wander through together. And as you breathe, the bridge in the distance is breathing too, expanding and contracting in the cool night air, waiting for the morning sun. The bridge is breathing. That is the image we left resting in the dark, and it is the one we will pick up now, gently, like lifting a smooth stone from still water. A bridge seems so solid, so permanent, so unmoving. When you stand beneath one or drive across one, the sheer mass of it suggests something that has forgotten how to move. Concrete and steel, rivets and beams, all locked together in a pose that looks as fixed as a mountain. But a mountain moves too, in its own way, over time so slow we cannot see it. A bridge moves faster than a mountain, though still slowly by our everyday measure. It moves with the heat of the day and the cool of the night. It stretches and shrinks. It is alive in the one way that all materials are alive. It responds to the world around it. And because engineers know this, they give the bridge room to breathe. They build in gaps, on purpose, places where the bridge is not fully joined to itself or to the land. Those gaps are what we are going to think about now, slowly, from one end to the other. If you have ever been in a car crossing a long bridge, you may have felt a rhythmic bump, a soft thump-thump-thump under the tires that did not feel like a pothole or a crack in the pavement. It felt deliberate, almost like a seam. That is exactly what it was. You were driving over an expansion joint. An expansion joint is a gap built into the bridge, usually where the bridge deck meets the road on solid ground, and sometimes at intervals along the bridge itself. The gap is often covered with interlocking metal teeth, like two combs facing each other with their tines overlapping but not quite touching. These metal fingers slide past each other as the bridge expands and contracts. When your car tire rolls over them, you feel that tiny dip and rise, that little click transmitted up through the wheels and the frame of the car. It is not damage. It is not something coming loose. It is the bridge doing exactly what it was designed to do, moving in its sleep. To understand why a bridge needs these gaps, we have to think about what happens to materials when they get warm or cold. Almost everything expands when it heats up and contracts when it cools down. This is a fundamental property of the physical world, true for steel, for concrete, for asphalt, for the metal rails of a train track, for the pipes that carry water under the street, even for the glass in a window. The atoms and molecules that make up a material jiggle a little more when they are warm, and they need a tiny bit more space. The change in size is very small for something the size of a spoon or a key. You would never notice it by looking. But when the object is enormous, when it is a bridge stretching hundreds or thousands of feet across open water, that tiny change per foot adds up to something you can measure in inches. In some cases, many inches. Imagine a steel beam, one single piece of steel, running the full length of a bridge. On a cold winter night, that beam is as short as it will ever be. When the morning sun hits it, the steel begins to warm. The warmth soaks into the metal slowly. The beam does not jump to a new length all at once. It creeps outward, a fraction of an inch at a time. By the hottest part of a summer afternoon, if the bridge is in a place with strong seasonal swings, that same steel beam might be several inches longer than it was on the cold winter night. Several inches is not a small amount in the world of large structures. If the beam had no room to grow, if it was locked tightly at both ends, those several inches of growth would have nowhere to go. The steel would press against whatever was holding it, and steel, for all its strength, can be overpowered by its own expansion. The force generated by thermal expansion is enormous, far greater than most people would guess. A steel rod heated by just a few degrees, if it is completely restrained, can push with a force of thousands of pounds. Over the length of a bridge, the numbers become staggering. The steel would eventually buckle, bending sideways out of its straight line, or it would crack, or it would push so hard against the abutments at the ends that the concrete would crumble. The bridge would tear itself apart, not because of any outside attack, but simply because it could not move. The expansion joint is the answer to this problem. It is a deliberate gap, a place where the bridge is allowed to grow and shrink without pushing against itself. Think of it as a deep breath. When you breathe in, your chest expands. The fabric of your shirt does not fight you. It has enough give, enough room, to let your ribs lift and your lungs fill. The expansion joint is the give in the bridge's shirt. When the bridge warms and lengthens, the gap narrows, the metal teeth sliding closer together. When the bridge cools and shortens, the gap widens, the teeth drawing apart. The movement is slow, silent, and completely regular. Day by day, season by season, the gap opens and closes like a slow eyelid, and the bridge stays whole. This same idea appears in many places beyond bridges, and once you start looking for it, you will see it everywhere. Sidewalks, for example. If you walk along a long concrete sidewalk, you will notice lines cut into the concrete at regular intervals. These lines are not decorative. They are joints, places where the concrete is intentionally separated so that it can expand and contract without cracking. Concrete, like steel, grows when it is warm and shrinks when it is cold. If a sidewalk were poured as one continuous slab with no joints, the first hot day would cause it to buckle upward, cracking into uneven slabs. The joints provide a controlled place for the movement to happen. The same is true for the concrete floors of large buildings, for the facades of skyscrapers, for the long metal pipes that carry steam or water through industrial plants. Anytime you see a long, solid-looking structure with regular gaps or lines, you are probably looking at an expansion joint, a place where the builders decided to let the material move rather than try to hold it still. Railway tracks offer one of the clearest and most dramatic examples. On a very hot day, If the rails are not installed with proper expansion gaps, the metal can heat up enough to buckle sideways. This is called a sun kink, and it produces a visible wiggle in the track, a section of rail that has pushed itself out of alignment because the force of its own expansion had nowhere else to go. A sun-kinked track is dangerous for trains, which need a smooth, straight, or gently curving rail to run safely. Modern railways use a variety of methods to manage thermal expansion. Some use expansion joints, gaps between lengths of rail that are cut at an angle so the train wheels pass over them smoothly. Some use continuous welded rail that is installed under specific tension, so that the rail is held in a state that can accommodate temperature changes without buckling. The engineers calculate the expected temperature range for the place where the track will lie, and they set the rail's neutral temperature, the temperature at which it is neither in tension nor compression, to be somewhere in the middle of that range. On a cold day, the rail pulls inward. On a hot day, it pushes outward. But because it started in the middle, the forces stay within what the steel and the fasteners can handle. It is another kind of breathing, managed by careful numbers rather than by visible gaps. Pipelines use similar strategies. A long pipeline carrying oil or gas across a desert or a tundra will change temperature dramatically, both from the weather and from the temperature of the fluid inside. If the pipeline were one continuous rigid tube, it would pull itself apart at the joints. So engineers build in expansion loops, U-shaped bends in the pipe, that can flex inward and outward as the pipe lengthens and shortens. These loops look like gentle kinks in an otherwise straight run, and they serve the same purpose as the metal teeth on a bridge expansion joint. They turn the linear push of thermal expansion into a gentle bending motion that the pipe material can handle without breaking. Even the glass in a window is given room to breathe. A window pane sits in its frame with a small gap around the edges, filled with a flexible sealant. That sealant keeps the water out, but lets the glass expand and contract with the temperature. Without that gap, the glass would press against the hard frame on a hot day and crack. But let us return to the bridge, because the bridge is where this principle becomes most visible and most personal. You feel the expansion joint in your car. Your body registers the tiny bump, and your brain, without even thinking about it, notes that something has changed, that the road surface has a seam. Most of the time, we ignore these sensations. They are part of the background texture of driving. But once you know what that bump is, it can become a kind of comfort. That little thump is the sound of the bridge breathing. It is the sound of a structure taking care of itself, moving the way it needs to move, so that it does not hurt itself. It is a small, regular, predictable noise, in a world that often feels neither small, nor regular, nor predictable. The design of an expansion joint is more careful than it might seem. The metal teeth, often made of steel, have to be strong enough to carry the weight of heavy trucks passing over them. They have to be shaped so that they do not catch tires or create a skidding hazard. They have to allow for movement in more than one direction, because a bridge does not only lengthen and shorten, it also twists slightly, tilts slightly, shifts slightly sideways under wind and traffic. A good expansion joint handles all these tiny movements without binding, without wearing out too quickly, and without making too much noise. Water and dirt are constant enemies. The gap is a place where rain can seep down and rust the steel underneath, so the joint often includes a rubber seal or a drainage channel to carry the water away. In cold climates, the joint has to keep working even when packed with ice or road salt. All of this thought goes into something most drivers experience as a half-second bump and then forget. There is a quiet lesson in the expansion joint, a lesson that applies far beyond bridges. The lesson is that strength is not always about being rigid. Sometimes the strongest thing you can do is to leave room, to build in a little give, to let the forces flow through and past, rather than trying to stop them dead. A bridge that fights its own expansion will destroy itself. A bridge that accepts its own need to move will stand for decades, for a century, for longer than a human lifetime. The gap is not a weakness. It is a kind of wisdom, built into the steel and concrete. A wisdom that says, I know I will change with the weather, and I am prepared for that change. This same wisdom appears in the design of the human body, though we rarely think of it that way. Your joints, your knees and elbows and knuckles, are gaps in the rigid structure of your bones. They allow movement. Without them, you would be a fixed, brittle frame, and the first attempt to bend would crack you. Your spine is a stack of small bones separated by soft discs, a series of tiny expansion joints that let you twist and bend and compress and stretch. The body breathes, the bridge breathes, the whole physical world breathes, expanding and contracting in a slow rhythm that goes on whether we notice it or not. On a hot day, you can sometimes see the evidence of thermal expansion with your own eyes. If you stand at one end of a long bridge and look along the railing, you might notice that the railing seems to shimmer, or that the joints at the ends are tighter than they were in the cool of the morning. This is not an illusion. The bridge is physically longer. The atoms in the steel are vibrating faster, pushing their neighbors a little farther away, and the cumulative effect of billions and billions of atoms all doing the same thing is a structure that has grown, measurably, since sunrise. By nightfall, as the air cools and the heat radiates away into the dark sky, the bridge will shrink back. The atoms will slow their vibration, settle a little closer together, and the gap will open again. This happens every day of the bridge's life, summer and winter, year after year. The bridge is never the exact same length twice. It is always in a state of gentle, ongoing adjustment. The next time you are in a car, and you feel that soft, rhythmic bump under the tires, you might let yourself notice it in a new way. Not as an interruption, not as a flaw in the road, but as a quiet signal. The bridge is saying hello. The bridge is letting you know that it is still breathing, still flexing, still doing what it was built to do. The sun has warmed it, or the night has cooled it, and it has moved just a little, and the gap you just crossed has narrowed or widened by some fraction of an inch. The bump is the sound of that movement finishing and beginning again, a cycle that started when the bridge was first built and will continue long after the car you are in has been retired and replaced. It is a kind of timekeeping, as steady as a heartbeat, as slow as the seasons. Now, as you lie here in the quiet, you might think about the bridges near where you live, or the bridges you have crossed in your life. Somewhere, right now, in the dark, a bridge is cooling down. The metal is contracting. The gap is widening by a distance smaller than the thickness of a fingernail. The stars are shining on the roadway. The river or the bay or the valley underneath is as dark as the sky. And the bridge is breathing, slowly, perfectly, exactly as it was designed to do. There is no hurry. There is no strain. There is only the quiet movement of materials responding to the temperature of the night, the gap opening and closing like a door that is never fully shut, like a slow breath held and released. And that same quiet movement is happening in the walls around you, in the floor under your bed, in the pipes behind the plaster. The whole built world is gently adjusting to the temperature, shifting by distances too small to feel. You are resting inside a breathing structure, just as the bridge rests inside its breathing steel. The gaps are everywhere, doing their silent work, keeping things whole by letting things move. You can let that thought settle over you like a second blanket. There is nothing to hold on to. There is nothing to fix. The bridges are breathing, and so are you. We left the ground for a moment, in our last quiet thoughts, and watched the bridge breathing below us. Now we are going to stay up in the open air a little longer, and turn our attention to something else that moves through the sky, an airplane. Not the whole airplane, with its roaring engines and its rows of seats and its small round windows. Just the wing, and not even the whole wing. Just the very tip of it, the place where the smooth metal curves upward like the turned-up end of a sled runner or the curled edge of a leaf. That little vertical fin at the end of the wing has a name. It is called a winglet, and its job is so quiet, so gentle, that you could fly 100 times and never think about it once. But it is doing something very clever up there in the thin, cold air. It is calming a swirl that you cannot see. To understand what a winglet does, we have to start with what a wing itself does, and we have to do it slowly, because the air is invisible and its movements can be hard to picture. A wing works by moving through the air. As it moves, it splits the air into two streams, one that goes over the top of the wing and one that goes under the bottom. The wing is shaped so that the air moving over the top has to travel a slightly longer path than the air moving under the bottom. Because the top air has to go farther in the same amount of time, it speeds up, and when air speeds up, its pressure drops. So you end up with lower pressure on top of the wing and higher pressure underneath. That difference in pressure pushes the wing upward. That upward push is called lift. It is what holds the airplane in the sky, countering the downward pull of gravity. Lift is not a thing you can hold in your hand. It is a relationship between shape and motion and air. The shape of the wing, curved on top and flatter on the bottom, is what makes this relationship work. That shape is called an airfoil, but you do not need to remember the word. You only need to picture the two streams of air, one fast and low pressure on top, one slower and high pressure on the bottom, meeting again at the back of the wing after having done their work. But air is a fluid, and like any fluid, it wants to move from areas of high pressure to areas of low pressure. It wants to balance itself out. At most places along the wing, this is not a problem because the wing itself is in the way. The solid metal skin of the wing keeps the high-pressure air below and the low-pressure air above separated. But at the very tip of the wing, there is no solid barrier. The wing just ends. And at that ending, the high-pressure air underneath sees its chance. It spills around the tip, curling upward into the low-pressure region on top. You can picture it like water curling around the edge of a paddle when you pull it through a pond, or like smoke curling around the corner of a building. The air does not just spill and then stop. It keeps moving, and the forward motion of the airplane combines with this sideways spill to create a spinning, twisting tube of air that trails behind the wingtip. This spinning tube is called a wingtip vortex. A vortex is just a swirl, a whirlpool in the air, rotating steadily as it stretches out behind the plane. If you could see it, a wingtip vortex would look like a long, tight spiral, a horizontal tornado spinning off the end of each wing. These vortices are not small. They can be quite strong, especially behind large, heavy airplanes. They trail behind the aircraft for miles, slowly sinking and drifting apart. This is why air traffic controllers keep planes separated by certain distances, especially near airports. The swirling wake left by one airplane can be strong enough to disturb the flight of a smaller airplane following too closely behind. That wake is the wingtip vortex, the same curl of air we are thinking about now. From the airplane's point of view, the vortex represents wasted energy. The engines have to burn fuel to push the plane through the air. Some of that fuel energy goes into creating lift, which is useful, but some of it goes into creating these swirling vortices, which is not useful at all. The vortices are a kind of leakage, a place where the neat pressure difference the wing worked so hard to create is spilling away into the empty sky. The stronger the vortex, the more energy is leaking, and the more fuel the plane has to burn to keep flying. Engineers have known about this leakage since the early days of aviation. The question was always whether anything could be done about it. The answer turned out to be a small change to the shape of the wingtip. By adding a vertical or angled fin at the very end of the wing, you can partially block the path that the high-pressure air would use to spill around to the top. The fin stands up like a small wall, and the spilling air hits it and is deflected, pushed back down or redirected in a way that weakens the vortex. A weaker vortex means less wasted energy, which means the airplane needs less fuel to fly the same distance. That is what a winglet does, in its most basic sense. It gently redirects the air rather than fighting it. It does not try to stop the spill entirely, because stopping it entirely would be impossible without a much larger and heavier structure. Instead, it just reduces the spill, calms the swirl, and lets the airplane slip through the sky a little more efficiently. The idea of adding something to the wingtip to reduce drag is not new. Early aerodynamicists thought about it, sketched it, tested it in wind tunnels. But winglets as we know them today, those graceful upswept tips you see on so many modern airliners, began to appear widely in the late 1980s. One of the first large commercial airplanes to use them prominently was the Boeing 747-400, which entered service around that time. The winglets on that airplane were a noticeable feature, standing up from the wingtips like small vertical stabilizers. They changed the look of the airplane in a way that even casual travelers noticed. Before that, most airliner wings just ended in a straight line, the metal simply stopping. Now, wings looked finished, as if someone had put a neat cap on the end. The change was aesthetic, but it was also functional. The winglets saved fuel. For an airline, saving even a small percentage of fuel on every flight adds up to enormous savings over the life of an airplane. And it also means less pollution, less carbon dioxide released into the upper atmosphere for every passenger carried. Since then, winglets and similar devices have become common. You will see them on small regional jets, on long-haul, wide-body airliners, even on some private and business aircraft. The exact shape varies. Some winglets are tall and thin, some are shorter and blended smoothly into the wing, a style called blended winglets. Some are split, with one part curving up and another part curving down. Some are so integrated into the wing shape that you might not even register them as a separate feature, just a subtle taper and curve at the very end. But they all do the same basic job. They calm the vortex. They reduce the leakage. They let the airplane fly a little farther on a little less fuel. The reason this works so well ties back to a very old principle of moving through fluids. When you move an object through air or water, the energy you spend can go either into useful work, like generating lift or pushing the object forward, or into stirring up the fluid, creating swirls and wakes and turbulence that serve no purpose. A good shape is one that minimizes the useless stirring. Fish are shaped the way they are, smooth and tapered, because a blunt shape would leave a large, messy wake and waste energy. Birds have wingtip feathers that separate and curve, acting like tiny individual winglets to reduce the vortex behind them. A soaring bird like an eagle or a vulture, riding thermals for hours without flapping, is a master of extracting lift from the air while leaving as little disturbance behind as possible. The winglet on an airliner is, in a sense, borrowing that same ancient solution, refined through millions of years of evolution and then redesigned by humans with wind tunnels and computers. There is something deeply calming about the idea of a winglet. It does not force the air. It does not bully it. It simply stands there at the end of the wing, quietly, offering the spilling air a different path, a gentler transition from high pressure to low. The air takes the offer. The vortex weakens. The energy that would have become a mile-long swirl in the sky instead becomes a little more forward motion, a little more lift, a little less fuel burned. It is a soft solution to a soft problem, an adjustment of shape rather than an addition of power. The airplane does not need a bigger engine to overcome the vortex. It just needs a slightly different wingtip. That is the kind of cleverness we are here to appreciate, the cleverness that hides in plain sight, that you can see from your window seat if you know to look for it. Next time you are on an airplane, if you find yourself with a window seat and the light is right, you might glance out at the wing. You will see the smooth metal stretching out from the body of the plane, the flaps and ailerons along the trailing edge, the paint and the markings and the small rivets. And at the very end, you will see the winglet, standing up or curving back, catching the sunlight. You might think about what is happening just beyond it, in the invisible air. The high pressure below, the low pressure above, the spill curling around the tip, the vortex starting to spin, and then being gently, quietly discouraged by that small upturned fin. The airplane is not just pushing through the sky, it is finessing its way through, smoothing its own path, leaving a slightly calmer wake behind it than it otherwise would. The winglet is a small thing, but it is doing its job every second of the flight, whether you are looking at it or not, whether it is day or night, clear sky or cloud. And now, as you lie here in the quiet dark, you might imagine that same gentle redirection happening in the air around you. Your breath moves in and out, a slow, steady flow. The air in the room settles around your shoulders, your arms, the curve of your head on the pillow. There are small currents, tiny movements of warmer and cooler air, drifting through the space. You do not need to control them or stop them. You can just let them be, let them find their own paths, let them curl and settle and calm. The same principle that shapes the wingtip shapes the world at every scale, from the vast spinning weather systems that cross the oceans to the tiny eddies of air that stir the dust motes in a sunbeam. Energy moves, it curls and swirls, and sometimes a small change of shape, a gentle curve, a slight upturn, is all that is needed to turn that swirling energy into something smoother, something quieter, something that lets the whole system rest a little easier. The winglet stands in the cold air at 35,000 feet, doing its quiet work right now, somewhere in the world. The night flights are crossing the oceans, their navigation lights blinking, their winglets slicing through the thin, dark air. The vortices trail behind them, weaker than they would have been, dissipating slowly into the wider atmosphere. The passengers inside are mostly asleep, their window shades drawn, their seats reclined, their dreams already underway. The winglets do not sleep. They do not need to. They just keep standing at the tips of the wings, calmly redirecting the air, flight after flight, mile after mile, a small, elegant solution to a problem most people will never know existed. And that, too, is a kind of restfulness. The world is full of quiet helpers, small shapes doing small jobs so smoothly that we never have to think about them. The winglet is one of them. The expansion joint on the bridge is another. And there are more, many more, waiting for us in the slow unfolding of these quiet hours together. We have thought about small things, the gap in the bridge deck, the upturned tip of the airplane wing. Now we are going to think about something larger, something that stretches across open water and seems to float there, held up by nothing but air and thin cables. A suspension bridge, the kind of bridge with tall towers and a long, sweeping curve of cable that droops between them like a loose clothesline, with the roadway hanging underneath. The Golden Gate Bridge is one of these. So is the Brooklyn Bridge. So are many of the longest bridges in the world. When you see one, the first question that comes to mind is the simplest one. Why does it not fall down? The towers look thin compared to the weight they are holding. The cables look almost delicate, like threads stretched across a vast space. And yet they hold up the weight of the roadway, and the cars and trucks on the roadway, and the wind that pushes against it all, and they do it day after day, year after year, through storms and heat, and the slow rusting work of salt air. The answer to why it does not fall down is an answer made of two simple, opposite ideas: pulling and pushing. And in a suspension bridge, the pulling and the pushing are separated, given to different parts of the structure, so that each part does the one thing it is best at. Let us picture the bridge first, before we name the forces. Imagine you are standing on the shore, looking out across the water. Two tall towers rise up from the water or from the ground, one on the near side and one on the far side. Between the towers, and beyond them to the anchorages on the shore, hang the main cables. These cables are not thin wires. They are thick bundles, sometimes several feet in diameter, made of thousands of individual steel wires bound together. They droop in a natural curve, the kind of curve a rope makes when you hold it at both ends and let it hang. That curve is called a catenary, but the name is less important than the feeling of it, the way it seems to be pulled down by its own weight into a shape that looks relaxed, settled, almost sleepy. From these main cables, smaller cables drop straight down at regular intervals. These are the suspender cables, and they hold up the roadway, the flat deck where the cars drive. The roadway runs from shore to shore, passing through the towers, supported by the suspender cables along its whole length. That is the picture. Two towers, two main cables drooping in their long curve, many vertical suspender cables hanging down, and the roadway riding on those suspenders like a hammock. Now let us think about weight. The roadway is heavy. The cars and trucks are heavy. All of that weight wants to go down, pulled by gravity. If you hung the roadway from the main cables with the suspender cables, the main cables would feel that downward pull. They would be tugged down at every point where a suspender cable attaches. That downward tug would pull the main cables tighter, would try to straighten out their curve. But a cable cannot be pushed. It can only be pulled, so when you pull down on the middle of a hanging cable, the cable resists by pulling back, by going tight, by stretching just a little. That state of being pulled is the first of our two simple forces. It is called tension. Tension is what you feel when you pull on a rope. Your hands move apart, the rope goes tight, and every fiber in the rope is being stretched, pulled end to end. The main cables of a suspension bridge are in tension. They are being pulled, constantly, by the weight of the roadway hanging from them, and they are good at being in tension. Steel is very strong in tension. It can be stretched an enormous amount before it breaks, far more than stone or concrete can. So the main cables are doing the job they are best suited for. They are holding the downward weight by pulling back, by staying tight, by being in a permanent state of stretch. But the cables do not float in the air on their own. They need to be held up. That is what the towers are for. The main cables drape over the tops of the towers, usually resting in saddles that let the cable slide just a little if it needs to. At the top of each tower, the main cable is pressing down. The whole weight of the roadway, transmitted through the suspender cables into the main cables, ends up pushing down on the towers. The towers are vertical. They stand straight up from their foundations, and the load that comes down on top of them is a squeezing load, a pressing load. The weight wants to crush the tower down into the ground. That state of being squeezed, of being pressed together, is the second of our two simple forces. It is called compression. Compression is what you feel when you push on a sponge. The material is being pressed inward from both ends. The tower of a suspension bridge is in compression. All that weight from the cables pushes down on it, and the tower pushes back up from its foundation. Every particle of the tower's steel or concrete is being squeezed, compressed, pushed together, and steel and concrete are both very good at being in compression. They can take enormous squeezing forces without crumbling. So the towers are doing the job they are best suited for, just as the cables are doing the job they are best suited for. This is the quiet, beautiful division of labor at the heart of a suspension bridge. The pulling forces go to the cables. The pushing forces go to the towers. Nothing is asked to do both. Nothing is asked to be strong in a way it is not naturally strong. The bridge takes a single problem, how to hold up a heavy road over empty space, and splits it into two smaller problems, pulling and pushing, and solves each one separately with the right material and the right shape. The main cables do not just end at the towers. They continue beyond the towers, sloping down to the ground on each shore, where they are anchored into enormous blocks of concrete or directly into solid rock. These anchorages are the third part of the system, the part that is easiest to overlook because it is mostly hidden in the earth. The anchorages take the tension from the cables and pass it into the ground. The cables pull on the anchorages, and the anchorages hold firm by being incredibly heavy, by being locked into the rock, by refusing to budge. Without the anchorages, the towers would be pulled over, the cables would snap free, and the whole system would unzip. The anchorages are the quiet anchors at the ends of the bridge's long pull, the places where the tension finally finds its rest. So we have three main parts, each doing one thing. The cables are in tension, being pulled along their whole length. The towers are in compression, being pushed down and squeezed. The anchorages are in resistance, holding the ends of the cables against the pull of everything in between. The roadway hangs from the suspenders, and the suspenders hang from the main cables, and the main cables hang from the towers and the anchorages, and the whole weight settles down into the earth. It is a long, slow pathway of force, and at every step, the force changes its nature to match the thing that must carry it. The Golden Gate Bridge, which opened in 1937, is one of the most famous examples of this system. Its two towers rise over 700 feet above the water. Its main cables are more than 3 feet in diameter and contain over 27,000 individual wires each. Those numbers are large, but you do not need to remember them. What matters is the feeling of them, the sense that something so enormous is held together by such a simple idea. The Golden Gate Bridge is painted a warm orange-red, a color called international orange, chosen partly because it stands out against the fog that often rolls through the strait. When the fog comes, the tops of the towers can disappear into the gray, and the roadway can seem to float in midair, held by nothing at all. But it is not held by nothing. It is held by tension and compression, by pulling and pushing, by forces that are as real as the steel itself, even though you cannot see them. Tension and compression are not just ideas for bridges. They are the two fundamental ways that any solid thing can carry a load. When you sit on a chair, your weight pushes down on the seat. The legs of the chair are in compression, being squeezed between the seat and the floor. If the chair has a back, and you lean against it, the back is in tension on one side and compression on the other, bending slightly under your weight. When you pick up a grocery bag by its handles, the handles are in tension, being pulled by the weight of the bag. The floor under your feet is in compression, being pressed down by your body. The bones in your legs are in compression. The tendons that attach muscles to bones are in tension. Every structure in the world, natural or built, carries its loads through some combination of pulling and pushing. A suspension bridge makes this combination unusually visible, unusually legible. You can stand on the shore and look at the Golden Gate Bridge and trace the forces with your eyes. The weight of the cars goes down into the roadway. The roadway hangs from the vertical suspenders, putting them in tension. The suspenders pull down on the main cable, putting it in tension along its curve. The main cable pulls down on the towers, putting them in compression. The main cable also pulls outward on the anchorages, putting them in tension with the ground. The pull goes down, then across, then down again, and finally sideways into the earth. The push goes straight down through the towers and into the bedrock below the water. It is a diagram you can see, a map of forces drawn in steel. And the bridge is never perfectly still. Like the expansion joints we thought about earlier, a suspension bridge moves. The cables expand and contract with the temperature. The roadway rises and falls slightly with the weight of traffic. The towers sway a little in the wind. The whole structure is alive with small motions, small adjustments, small breaths. The tension in the cables is not a fixed number. It changes slightly from hour to hour, day to day, as the temperature changes and the traffic comes and goes. The compression in the towers changes too. But the bridge is designed for these changes. The materials can handle them. The forces stay within the range that the steel and concrete can bear. The bridge breathes, just as the smaller bridges breathe through their expansion joints. But here the breathing is distributed through the whole system, a slow, ongoing conversation between pull and push. At night, the Golden Gate Bridge is lit by small lights along the cables and the towers, and it glows against the dark water. The fog might roll in, softening the lights into blurred halos. The cars cross less frequently. The bridge settles into a quieter state, holding mostly its own weight, resting. But the tension does not go away. The compression does not go away. The bridge is always working, even at 3 in the morning, when no one is crossing it. Its own weight is enormous, and holding up that weight is a full-time job. The cables are always tight. The towers are always compressed. The anchorages are always resisting. The bridge never sleeps, any more than the winglet on the airplane sleeps. It just keeps doing its quiet work, separating the pull from the push, giving each one to the part that can handle it best. And now, as you lie here in the dark, you might feel your own body in these terms, just for a moment. The weight of your body is pressing down into the mattress, and the mattress is pressing back up. That is compression. If you stretch your arms out and let your hands hang, the muscles and tendons in your shoulders are in tension, being pulled by the weight of your arms. Your spine is a tower of bones in compression, with soft discs between them acting as small shock absorbers. Your breath pulls your chest open and then lets it relax, a slow cycle of tension and release, tension and release. The whole body is a suspension bridge in miniature, a balance of pulls and pushes, holding you up without you having to think about it. The fog is still out there over the Golden Gate Strait or over whatever water lies beneath whatever bridge is nearest to your thoughts. The towers rise up through the mist. The cables hang in their long, patient curve. The pull and the push are in balance. Nothing is straining. Nothing is about to break. The bridge is holding itself up by knowing exactly what to pull and exactly what to push. And you are holding yourself here, in this moment, without effort, without strain, just resting in the balance that is already there. We have been thinking about balance. The balance between pull and push in the cables and towers of a bridge. The balance between high pressure and low pressure on the wing of an airplane. The balance between expansion and contraction in the gaps of a bridge deck. Now we are going to think about a different kind of balance, one that involves movement. Not the slow, invisible movement of metal heating and cooling, but a larger, more visible movement, the kind you can feel if you are standing in the right place at the right time. We are going to think about tall buildings, skyscrapers, and why they are built to sway. A skyscraper looks as solid as anything humans have ever made. Steel frame, concrete core, glass skin, standing hundreds of feet above the city street, so heavy and so fixed that it seems to belong more to the earth than to the air. But the air pushes on it. The wind, which seems so light when it brushes your face, becomes a powerful force when it acts on a surface the size of a building's side. A tall building is like a huge sail, catching the wind across thousands of square feet of glass and steel. The wind does not push evenly. It gusts, it swirls, it rises and falls in strength from moment to moment. And the building, for all its weight, responds to that push. It moves. Not much, not enough to be frightening or even noticeable, unless you are paying very close attention, but it moves. And that movement is not a sign that something is wrong. It is a sign that something is exactly right. The alternative to swaying is rigidity. A building that tries to stand perfectly still against the wind, that has no give at all, is a building that is fighting the wind with every fiber of its being. And the wind, over time, will find the weak point in that fight. Materials can only take so much repeated bending before tiny cracks begin to form. If the building cannot release the wind's energy in some way, that energy stays in the structure, building up until something gives. A rigid building is a brittle building. A building that can flex, that can sway a little and then come back to center, is a building that is letting the wind's energy flow through it and away, rather than trapping it inside. This is the same wisdom we saw in the bridge expansion joint, the wisdom of leaving room for movement. Only here, the movement is not a slow thermal breath. It is a quicker, livelier motion, a dance with the wind. When a gust of wind hits a skyscraper, the building leans just slightly in the direction the wind is pushing. The steel frame bends. The concrete core flexes. The people inside might feel a tiny sense of motion, like being on a boat that has been nudged by a very small wave. Then the gust passes, and the building swings back. But it does not just stop at the exact upright position. Like a pendulum, it overshoots a little, then swings back the other way, then back again, with each swing smaller than the last, until it returns to rest. This is called oscillation, the natural back and forth motion of something that has been pushed and then released. Every tall building has a natural frequency, a speed at which it likes to oscillate, determined by its height, its weight, and how stiff it is. The engineers who design the building calculate this frequency and make sure that the wind, even in its strongest gusts, will not match that frequency too closely. If the wind's push matched the building's natural rhythm, the sway could build up over time, each gust adding a little more energy, until the movement became uncomfortable or even dangerous. This is called resonance, and avoiding it is one of the central tasks of skyscraper design. To manage all of this, engineers have a few different strategies. The first and most basic is to make the building stiff enough that its sway stays very small, well within the range that people can tolerate without noticing. The steel frame and the concrete core work together to provide this stiffness. But for very tall buildings, stiffness alone is not always enough, or it would require so much extra steel and concrete that the building would become impractical. So engineers sometimes add a second strategy, a device that actively works against the sway, that pushes back in the opposite direction at just the right moment. This device is called a tuned mass damper. A tuned mass damper is, at its most basic, a very large weight placed near the top of a building, suspended so that it can swing freely. When the building sways to the left, the weight keeps moving to the right for a moment, pulled by its own inertia. When the building sways to the right, the weight lags behind and swings left. The weight is connected to the building's frame with hydraulic pistons or other mechanisms that convert this swinging motion into a controlled push against the building's movement. The weight does not stop the building from swaying. What it does is change the rhythm of the sway, dampening it, turning a sharp, uncomfortable motion into a slower, gentler one. It absorbs some of the wind's energy and dissipates it as heat, a tiny amount of warmth that radiates away into the air. The damper is tuned, meaning its weight and the length of its swing are carefully chosen to match the building's natural frequency, so that it pushes back at exactly the right time to calm the motion. The most famous example of a tuned mass damper is in Taipei 101, a skyscraper in Taiwan that was the tallest building in the world when it was completed in 2004. Near the top of that building, suspended between the 87th and 92nd floors, hangs a huge steel sphere. It weighs about 660 metric tons. It is made of stacked steel plates welded together, and it is roughly 18 feet in diameter, a golden ball that visitors to the observation deck can actually see, hanging in the center of the building like a giant pendulum. When a typhoon brings strong winds to Taipei, or when an earthquake shakes the ground, that sphere swings into action, moving opposite to the building's motion, calming it, steadying it. The building sways, but the people inside feel less of that sway than they otherwise would. The sphere is doing the work of a shock absorber, a damper, a gentle hand on the shoulder of the building saying, "Steady now, easy now." Not all tall buildings have a visible tuned mass damper. Some have dampers that are hidden inside mechanical rooms, or they use different systems entirely. Some buildings have tanks of water near the top that slosh back and forth, using the same principle but with liquid instead of a solid weight. Some use active systems with motors and sensors that detect the building's movement and push against it in real time. But the basic idea is always the same. You add a weight that can move independently of the building, and you tune it so that its movement cancels out some of the building's own movement. It is a duet, a partner dance, the building and the weight moving together in a way that makes the combined motion smaller and smoother than the building's motion alone. This idea of a tuned mass damper is not unique to skyscrapers. It appears in many places where unwanted vibration needs to be controlled. Cars have small tuned mass dampers in their frames to reduce road vibration. Power lines sometimes have small weights attached to keep them from vibrating too much in the wind. Even some bridges have them. The Millennium Bridge in London, a pedestrian bridge that opened in 2000, developed an unexpected sway when large crowds walked across it. The slight side-to-side motion caused people to unconsciously synchronize their steps, which made the sway worse, which made more people synchronize, in a feedback loop. The bridge was closed and retrofitted with tuned mass dampers, and the sway was calmed. The dampers are still there now, hidden under the walkway, doing their quiet work. What makes all of this so restful to think about, as you lie here in the dark, is that the sway is not a flaw. It is not a mistake that engineers are trying to eliminate. It is a fundamental part of how tall things stay standing. A tree sways in the wind, a grass blade bends, a bird's wing flexes. Rigidity is rare in nature, and for good reason. The world is full of forces that push and pull and gust and swirl, and the things that survive those forces are the things that know how to give a little. A skyscraper is just a tree made of steel and glass, rooted in the ground, swaying in the breeze, letting the wind pass through its branches without breaking them. And there is something deeply calming in the image of that heavy sphere hanging in the dark near the top of Taipei 101. Late at night, when the offices are empty and the observation deck is closed, the building still sways gently in the wind. The sphere still swings, silent and patient, its steel plates cool in the darkness, its hydraulic pistons barely hissing as they move. The wind blows across the city, and the building leans, and the sphere leans the other way, and the two of them together settle back toward stillness. This is happening right now, somewhere in the world. It is happening in Taipei, and it is happening in other tall buildings in other cities, wherever the wind is blowing and the dampers are working. The sway is not a problem to be solved. It is a rhythm, a slow breath, a quiet dance that goes on all night while the city sleeps. You might feel, as you lie here, that you are swaying too, just a little. Not in a physical sense, but in the sense that your own thoughts drift and return, like a building swinging back toward center. The mind has its own natural frequency, its own way of settling after being pushed by the gusts of the day. A worry comes, and you lean into it, and then it passes, and you swing back. A memory rises, and you sway toward it, and then it fades, and you return. The tuned mass damper in the building is not so different from the quiet part of your own awareness that notices a thought and gently lets it go, that feels a tension and softens around it, that knows how to come back to rest without forcing anything. The building sways, the damper swings. The wind blows and then it doesn't. The whole structure is designed for this, designed to move, designed to flex, designed to take whatever the sky gives it and return, always, to center. You are designed that way too. Your body knows how to settle. Your breath knows how to find its rhythm. You do not have to hold yourself rigid against the night. You can sway, just a little, in the gentle current of your own tiredness, and let that tiredness carry you towards sleep, the way the wind carries the building a few inches to the left, and then lets it go. The damper is working. The building is steady, and you are steady too, held in the same quiet balance that holds up the towers and the cables and the great glass walls that catch the last light of the evening and then let it go. We have spent time with large things, with bridges and towers and buildings that scrape the sky. Now we are going to step inside one of those tall buildings, into a small room that moves, an elevator. The elevator is something so ordinary that you probably do not think about it even when you are inside one. The doors slide shut. You feel a slight pressure in your ears, or a small lurch in your stomach. The numbers above the door light up one after another, and then the doors open, and you are somewhere else, higher or lower than you were before. The whole thing happens so smoothly, so reliably, that it is easy to forget how strange it actually is. A metal box, carrying people, rising straight up through a vertical shaft hundreds of feet tall, stopping exactly at the right floor, thousands of times a day, year after year, without incident. How does it do that? And why does the motor that runs it not have to be as enormous as the building itself? The answer, like so many answers in engineering, comes down to balance. Not the balance of pull and push this time, but the balance of weight against weight. An elevator works by using a counterweight, a heavy block that rides up and down on the opposite side of the cables, offsetting most of the weight of the elevator car and its passengers. The motor only has to lift the difference between the two, not the whole load. It is a seesaw with one side nearly as heavy as the other, so that a modest push can tip it either way. Let us picture the system from the beginning. An elevator has a car, the box you stand in. That car is attached to the end of a set of strong steel cables. The cables rise up from the top of the car, pass over a large wheel called a sheave at the very top of the shaft, and then drop down the other side. On that other side, the cables are attached to a heavy weight, the counterweight. The counterweight is made of steel or cast iron plates stacked inside a frame, and its total weight is carefully chosen. It is usually set to equal the weight of the empty elevator car plus about 40 to 50% of the maximum passenger load. In other words, when the elevator car is carrying an average number of people, it weighs about the same as the counterweight on the other side. The sheave at the top is connected to an electric motor. When the motor turns the sheave, the cables move, and the car and the counterweight trade places. If the car goes up, the counterweight goes down. If the car goes down, the counterweight goes up. The motor is not lifting the car against gravity all by itself. It is mostly overcoming the slight difference in weight between the two sides, plus some friction in the system. If the car is heavier than the counterweight, the motor has to pull a little harder to lift it, or it has to brake a little to lower it. If the car is lighter, the motor has to pull to lift the counterweight, or brake to lower it. Either way, the motor is only dealing with a fraction of the total weight it would have to lift if the counterweight were not there. This is a quiet, clever kind of efficiency. An elevator in a tall building might weigh several thousand pounds empty and carry another several thousand pounds in passengers. Without a counterweight, the motor would need to be powerful enough to hoist that entire weight up the full height of the shaft, and it would need to be strong enough to stop it on the way down. The motor would be huge, the energy use would be enormous, and the whole system would be much more expensive and much less practical. With a counterweight, the motor can be much smaller, the energy use is much lower, and the cables and the sheave and the brakes all have an easier job. The counterweight does the heavy lifting, so the motor does not have to. There is another piece of quiet cleverness in the elevator, one that has nothing to do with the motor, but everything to do with why we feel safe stepping into one. It is the safety brake. The modern elevator safety brake was invented by a man named Elisha Otis in the middle of the 19th century. Before his invention, elevators existed but were used almost entirely for freight. People did not trust them. The fear was straightforward. If the cable snapped, the car would fall. And cables did sometimes snap. In 1852, Elisha Otis demonstrated his safety brake at the Crystal Palace exhibition in New York. He stood on a platform hoisted high above the crowd, and he had an assistant cut the rope holding the platform up. The platform dropped for a split second, and then it stopped, caught by a mechanism that had sprung into action. Otis called out to the crowd, "All safe, gentlemen, all safe." That demonstration changed the history of buildings. It made the passenger elevator possible, and the passenger elevator made the skyscraper possible. Before the safety elevator, buildings rarely rose above 5 or 6 stories, because people would not walk up more stairs than that. After the safety elevator, buildings could go as high as engineers could build them. The mechanism Otis invented is still used, in more advanced forms, in elevators today. It works by using the speed of the car to trigger a braking action. If the car begins to descend too quickly, faster than its normal maximum speed, a governor device senses the overspeed and activates a set of wedges or jaws on the sides of the car. These wedges are forced against the guide rails that the elevator rides on, and the friction stops the car in place. The brake does not depend on the cable at all. It works even if the cable is completely severed. It is a second line of defense, a backup system that sits quietly, waiting, and is almost never needed, but is always there. There is something reassuring about that, especially in the quiet of the night. All over the world, in dark office towers and sleeping apartment buildings, elevators are resting in their shafts. The counterweights hang motionless on their cables. The safety brakes are poised, ready but inactive. The motors are silent. The whole system is at rest, balanced, waiting for morning. The balance that keeps the elevator efficient is the same balance that keeps it still. The car and the counterweight are so nearly equal in pull that neither one wants to move on its own. Gravity holds them in place, each one canceling the other out, like two people of equal weight sitting perfectly still on a seesaw. And when the morning comes and the first person steps into the elevator car, the balance shifts by just that person's weight. The motor feels the difference and wakes up, turning the sheave just enough to compensate. The car rises, and the counterweight sinks, and somewhere in the middle of the shaft they pass each other in the dark, one going up, one going down, trading places in a slow, steady rhythm that will continue all day. Hundreds of trips, thousands of feet of vertical travel, and at the end of the day, the car settles at the ground floor, the counterweight hangs near the top of the shaft, and the balance returns to its resting state. This idea of using a counterweight to balance a load is not unique to elevators. You can see it in many places once you start looking. A drawbridge, the kind that lifts up to let boats pass, often has large counterweights at its base that swing down as the bridge leaf swings up, making the lifting easier. A crane uses counterweights at its rear to keep from tipping over when it picks up a heavy load at its front. A window sash in an old house often has small counterweights hidden inside the wall, connected to the window by cords over pulleys, so that you can lift the heavy window with one hand. Even the human body uses a form of counterbalancing when you lean forward and your hips shift back to keep you from falling over. Balance is everywhere, doing its quiet work, making heavy things feel light. Elisha Otis did not invent the elevator. He invented the safety brake that made the elevator trustworthy, and his invention, combined with the counterweight system, created the vertical city we live in today. Every time you step into an elevator and press a button, you are relying on principles that were worked out more than a century and a half ago. The counterweight balances the load. The motor overcomes the small difference. The safety brake waits in case it is needed. And the whole system is inspected, maintained, and tested so regularly that the chance of anything going wrong is vanishingly small. The elevator is, statistically, one of the safest ways to travel, safer than stairs, safer than escalators, safer than cars. It is a quiet marvel that most people use without a second thought. And there is a deeper kind of balance here too, a balance between what we see and what we do not see. When you are in an elevator, you see the polished metal doors, the handrail, the panel of buttons, the little screen that shows the floor number. You do not see the counterweight sliding down the shaft on the other side of the wall. You do not see the sheave turning at the top of the building. You do not see the safety brake waiting in its housing. All the cleverness is hidden, tucked away behind panels and walls, doing its job in the dark. That is the way of so many things we have thought about together. The gaps in the bridge are hidden in plain sight. The winglet works in air you cannot see. The tuned mass damper swings inside a sealed room near the top of a skyscraper. The counterweight rides silently in its shaft, never seen, never thought of, always working. Now, as you lie here, you might feel the weight of your own body sinking into the mattress, and you might think about the balance that holds you there. Gravity pulls you down. The mattress pushes back up. The two forces are equal, and so you do not move. You are at rest, perfectly counterbalanced, like an elevator parked at the ground floor in the middle of the night. Your breathing is the only motion, the small rise and fall of your chest, a gentle lifting and lowering that requires no motor at all. The day's weight has been lifted from you, or maybe it is more accurate to say that it has been balanced by the quiet of the night, each worry offset by the stillness around it. You do not have to carry anything right now. You can let the counterweight do its job. You can rest in the balance that is already there, holding you steady, holding you safe, asking nothing from you but this slow, easy drift toward sleep. We have been up in the air, on bridges and in tall buildings, and inside elevator shafts. Now we are going to come all the way down to the ground, to something so ordinary that you walk on it, drive on it, and cross it every day without ever thinking about its shape. A road. A road looks flat, When you stand at one end and look down its length, it seems like a smooth, level ribbon of asphalt or concrete, stretching out in front of you with no features except the painted lines. But a road is not flat. It is almost never flat. It has a gentle curve, a slight rise in the middle, and a slight fall toward the edges, so subtle that you cannot see it just by looking. If you could take a cross-section of a typical road, a slice through it from one side to the other, you would see that the surface forms a very low, very wide arc, like the top of a very large circle. This shape has a name. It is called a camber, or sometimes a crown, and its job is to move water out of the way. Water is one of the quiet enemies of roads. It seems harmless enough. Rain falls, it wets the surface, and then it dries. But water that sits on a road, that pools in low spots and does not drain away, causes two kinds of trouble. The first is immediate and dangerous. When a car drives over standing water at speed, the tires can lose contact with the road surface and skim across the top of the water. This is called hydroplaning. When a car hydroplanes, the driver loses the ability to steer or brake. The vehicle is essentially sliding on a thin film of water, and until the tires can push through that film and grip the road again, the driver is just a passenger. Hydroplaning is most likely to happen when water is deep enough to overwhelm the tire's tread. But even a thin sheet of water can cause problems if the road is perfectly flat and the water has nowhere to go. The second kind of trouble is slower, but just as real. Water that sits on a road seeps into tiny cracks in the surface. Over time, especially in climates where the temperature goes below freezing, that water can freeze and expand, widening the cracks. Freeze-thaw cycles are one of the main reasons roads develop potholes. Water gets in, freezes, pushes the material apart, then melts and leaves a larger gap for more water to enter. Over many cycles, the road surface breaks down. Keeping water off the road, or moving it off as quickly as possible, extends the life of the pavement by years. So roads are built with a camber, a gentle slope from the center down to the sides. On a straight section of road, the highest point is the center line, or sometimes slightly to one side if the road is a divided highway. From that center line, the road slopes downward at a very shallow angle, usually something like 2 or 3%, which means the road drops 2 or 3 inches for every 100 inches of horizontal distance. That is almost nothing. You would never feel it walking or driving, but it is enough for water to flow. Rain hits the crown in the middle and runs downhill, toward the edges, where it collects in gutters or drainage ditches and is carried away. The road dries faster. The risk of hydroplaning goes down. The freeze-thaw damage is reduced, all because of a curve so gentle that most people go their whole lives without knowing it is there. The camber is not the same on every part of the road. On a curve, the road is often banked, tilted so that the outside edge is higher than the inside edge. This is called superelevation, and its purpose is different from the camber. A banked curve helps cars go around the turn by tilting them slightly inward, counteracting the centrifugal force that wants to push them outward. But even on a banked curve, the cross-section still has a slight crown for drainage, because the engineers have to manage both the turning forces and the water at the same time. The shape of a road is more complex than it looks, a careful balancing of slope and curve and elevation that changes subtly from one section to the next. This same principle of a gentle curve for drainage appears in many other places you might not think about. A running track at a school or a stadium looks flat from the stands, but it has a slight crown or is sloped just enough to let rain run off to the inside or the outside, depending on the design. A rooftop on a house is not flat, even if it looks flat. It has a very slight pitch, a slope that carries water toward the edges and into the gutters. The pitch might be as little as 1/4 of an inch per foot, barely visible, but enough to keep water from pooling and leaking through the roof. A tennis court, a basketball court, a parking lot, all of them have subtle slopes that move water toward drains. The next time you are in a large parking lot after a rain, look at the pattern of wet and dry patches. The high spots dry first, the low spots hold puddles. The whole lot is shaped to channel water toward the drains, and that shaping was done on purpose, with careful grading and planning, long before the asphalt was poured. The word camber comes from an older word meaning curved or arched, and it has been used in road building for centuries. The Romans, who built roads that are still visible 2,000 years later, understood the importance of drainage. Their roads were raised in the center and sloped toward the sides, with ditches along the edges to carry the water away. They knew that water was the enemy of stone and gravel, that a dry road was a durable road. The same knowledge guided the builders of the first modern highways and continues to guide road engineers today. The materials have changed, from stone blocks to asphalt and concrete, but the shape remains essentially the same, a low arch against the rain. There is a quiet pleasure in noticing the camber of a road once you know it is there. On a rainy day, you can watch the water flow across the surface, finding its way to the lowest point, following the invisible curve that the engineers built into the pavement. The water does not hesitate. It knows where to go because the shape tells it. The road, which seemed so flat and unremarkable, reveals itself as a carefully designed surface, a shallow funnel that directs thousands of gallons of rainwater off to the sides, keeping the tires of the cars in contact with the ground. The painted lines on the road, the lane dividers and the edge stripes follow the crown as well, rising and falling with the same gentle curve. Everything on the road is shaped by this need to move water, even if the shaping is too subtle to see. And there is a metaphor here, if you want one, about the small adjustments that keep life flowing. The camber is not dramatic, it does not call attention to itself. It just tilts the road enough to let the water run off, so that the road stays solid and safe. In the same way, a small change in the angle of your thoughts, a slight tilt away from something that is pooling and causing damage, can be enough to let the stress drain away. You do not need a steep slope. You do not need a grand gesture. A 2% grade is enough, just enough tilt to let the water run. Now, as you lie here, you might think about the roads you traveled today or yesterday, or any day that comes to mind. They are out there in the dark right now, empty or nearly empty, curving gently under the streetlights. If it is raining where you are, or if it rained earlier, the water is running off the crown of the road, finding the gutters, flowing into the drains, disappearing into the pipes below the street. The road surface is drying. By morning it will be ready for the day's traffic, its shape unchanged, its camber still doing the job it was built to do. And if it is not raining, the road is simply resting, holding its shape, waiting for the next time it is needed. The crown is there, invisible, patient, a quiet piece of cleverness that asks nothing from the people who drive over it, except that they never have to think about it at all. The same is true of so many things we have explored together. The expansion joint that lets the bridge breathe, the winglet that calms the swirling air, the cables and towers that trade pull for push, the damper that sways against the building's sway, the counterweight that balances the elevator car. All of them are shaped for a purpose, curved or gapped or weighted in ways that do their work silently, without fuss, without thanks. The camber of the road belongs in that family. It is a small, elegant answer to a simple problem, and it has been doing its job for thousands of years, on roads made of stone and roads made of asphalt, in every country, in every climate, every time it rains. You can let the image of that gentle curve settle into your mind. A road at night, empty, slightly shining from a recent rain. The water has already run off to the sides, the surface is nearly dry. The streetlights reflect in the damp patches near the gutters. The crown of the road is doing its work, and the road is quiet, and the cars are parked, and the whole built world is resting, tilted just enough to let the day's weather slide off into the dark. You are resting too, tilted just enough towards sleep to let the last thoughts of the day slide away, finding their own channels, draining off into the quiet. The road is dry, the night is still, and there is nowhere you need to go. We have followed water off the road, down the gentle camber, into the gutters and the drains. Now we are going to follow it to a much larger place, a place where water is not just flowing off a surface, but pressing against one with enormous weight. A dam, a wall of concrete or earth built across a river valley, holding back a lake. The lake might be miles long, deep and still, reflecting the sky and the surrounding hills. All of that water, millions and millions of tons of it, wants to move. Gravity pulls it downhill, toward the sea, and the only thing stopping it is the dam. How does a wall, no matter how thick, hold back an entire lake without being pushed over, without sliding downstream, without cracking under the pressure? The answer, as with the suspension bridge, is a combination of two things: weight and shape. A dam resists the water partly by being very heavy and partly by being very cleverly curved. The best example to think about is the Hoover Dam, on the border between Nevada and Arizona in the United States. It was completed in 1936 during the Great Depression, and it is one of the most famous dams in the world. It stands in the Black Canyon of the Colorado River, a wall of concrete rising more than 700 feet from the riverbed. Behind it stretches Lake Mead, a reservoir that holds enough water to cover the entire state of Pennsylvania to a depth of about 1 foot, to use a comparison that engineers sometimes make. That is a staggering amount of water, a weight that is almost impossible to comprehend. And yet the dam stands there, year after year, holding it all back without any motors, without any pumps, without any moving parts at all. It holds back the lake simply by being what it is, a heavy, curved wall wedged into a narrow canyon. The first thing to understand is the weight. The Hoover Dam is what is called a gravity dam. A gravity dam works by being so heavy that the force of friction between its base and the rock underneath is greater than the force of the water pushing against it. The water pushes horizontally, trying to slide the dam downstream. The dam's weight pushes vertically, pressing it down into the ground. That downward force creates friction, a gripping force, between the bottom of the dam and the bedrock. As long as the downward force is large enough, the friction will hold the dam in place, and the water will not be able to budge it. The Hoover Dam contains about 3.25 million cubic yards of concrete. That concrete is dense, heavy, and it just sits there, day after day, pressing down into the earth with a force that far exceeds the push of the lake. The water pushes. The dam pushes back with its own weight. The dam wins. But weight alone is not the whole story. The Hoover Dam is also curved. If you look at it from above, or from the downstream side, you can see that it bends in a graceful arch, curving into the reservoir. This is not just for looks. The curve turns the dam into an arch dam as well as a gravity dam. An arch works by taking a load that pushes against its face and transferring that load sideways into the walls at either end. Think of a stone arch bridge, the kind the Romans built. The weight of the bridge and the traffic pushes down, but the curve of the arch turns that downward push into a sideways push, compressing the stones together and passing the force into the abutments on the banks. An arch dam works the same way, except the load is horizontal, pushing from the water side. The curve of the dam takes that horizontal push and squeezes it sideways into the canyon walls. The dam is wedged between two solid rock cliffs, and the harder the water pushes, the tighter the dam presses itself into the rock. The water's own force helps lock the dam in place. So the Hoover Dam uses both principles together. Its weight presses it down, creating friction that resists sliding. Its curve presses it sideways, creating compression that resists tipping and cracking. The two forces work together, and the combination is far stronger than either one would be alone. The concrete itself does not have to be strong enough to resist the entire force of the lake, as if it were a flat wall standing alone. The shape of the dam shares the load with the canyon, and the weight of the dam shares the load with the earth. It is a cooperative effort, the dam and the rock working together, each doing what it is best at. The water, for its part, is relentless. The pressure at the base of the dam is immense, because water pressure increases with depth. Every foot of depth adds more weight of water pressing sideways. At the base of the Hoover Dam, the pressure is something like 45,000 pounds per square foot. That is enough to shoot a jet of water out of a small opening with enough force to cut through steel. But the dam is thickest at the base, more than 600 feet thick, tapering to only about 45 feet thick at the top. The shape matches the pressure, thick where the force is greatest, thin where the force is least. The dam uses its material efficiently, putting concrete only where it is needed, saving millions of tons of material compared to a dam that was uniformly thick from top to bottom. There is something deeply calming about the way a dam works, because it works by doing nothing. It has no moving parts. It consumes no fuel. It does not turn on or off. It simply stands there, heavy and curved, and lets the forces of nature flow around it and through it. The water presses. The dam resists. The water evaporates from the surface of the lake, condenses into clouds, falls as rain somewhere else, and eventually flows back to the river. The dam does not change. It does not weaken, at least not on any timescale that matters to a human life. The concrete will last for centuries, maybe longer. The curve will hold, the weight will hold. The quiet standoff between the lake and the wall will continue, day and night, summer and winter, storm and calm. Building the Hoover Dam was an enormous undertaking, and the engineers had to solve problems that went far beyond just stacking concrete in a canyon. They had to divert the Colorado River around the construction site by blasting 4 huge tunnels through the canyon walls. They had to pour the concrete in stages, using cooling pipes to carry away the heat generated by the curing concrete, because if the concrete had cured all at once, the heat would have caused it to crack. The dam is not a single monolithic block. It is a series of vertical columns interlocked with grooves and filled with grout, so that each column could cure and shrink independently without pulling the whole structure apart. Even now, the dam is not completely still. It shifts very slightly with the temperature, expanding in the desert heat and contracting in the cool of the night. But these movements are tiny, accounted for in the design, absorbed by the joints between the columns. At night, the Hoover Dam is a quiet place. The tour buses have left. The generators in the power plant hum steadily, turning the force of falling water into electricity. The water slides through the intake towers, down through the penstocks, through the turbines, and out into the river below. The process is smooth and continuous, a steady conversion of potential energy into electrical energy. The lake behind the dam is dark and still, reflecting the stars. The dam face is cool to the touch, radiating the day's heat back into the desert air. A few lights shine on the top, marking the road that crosses from one state to the other. The curve of the arch is visible if you stand in the right place, a sweeping line of concrete against the black rock of the canyon, and the water keeps pressing, and the dam keeps resisting, and the balance holds. This balance is not unique to the Hoover Dam. Every dam, whether it is a massive concrete gravity arch dam or a simple earthen embankment across a small stream, works by managing the same forces. An earthen dam uses sheer bulk to hold back water, with a wide base and gentle slopes. A buttress dam uses a series of supports on the downstream side to brace a relatively thin wall. An arch dam, like the Hoover Dam but with less reliance on weight and more on shape, can be incredibly thin for its height, sometimes only a few feet thick at the crest, because the curve does almost all the work. The choice of dam type depends on the shape of the valley, the strength of the rock, the availability of materials, and the purpose of the dam. But the underlying principles are always the same. Weight resists sliding, shape resists tipping. Together they let a wall of concrete or earth stand up to a force that would flatten any ordinary building. There is a quiet lesson in the dam, a lesson about how to handle pressure. The dam does not fight the water actively. It does not push back with equal and opposite emotion, the way a person might. It simply stands in the way, heavy and still, and lets the water exhaust its energy against an immovable object. The water is strong, but it is also fluid, flexible, always finding the path of least resistance. The dam does not give it a path. The dam is patient. It has nowhere else to be. It can wait for centuries, and it does. Now, as you lie here, you might think about the pressures that have built up during your day, the weight of tasks and worries and conversations, and you might imagine them as water pressing against a wall. You can be the dam, but not in the sense of fighting back. You can be the dam in the sense of being still, of being heavy with tiredness, of letting the pressure expend itself against your quiet presence without moving you. The lake is there, the water is deep, but you are curved in a way that channels the force elsewhere, into the solid walls of the night around you. You do not have to hold the water back by effort. You just have to rest in your own weight, your own shape, your own quiet resistance to anything that would disturb this slow drift toward sleep. The dam stands in the dark canyon. The lake is calm. The river flows quietly downstream, its work done, its energy spent. And you are still, and the pressure is just pressure, and it cannot move you. We have stood at the base of a dam and felt the weight of the water pressing against the concrete. Now we are going to move to something much smaller, something you can touch with your hand. An airplane window. If you have ever sat in a window seat on a commercial airliner, you have looked through one of these. It is not very big, just large enough to rest your head against and watch the ground fall away or the clouds drift past. And it is round, or more precisely oval, with no sharp corners anywhere. The shape is so familiar that you probably do not question it. But there was a time when airplane windows were not round, they were square. And the story of why they became round is a quiet, careful story about how materials fail, and how engineers learn from failure, and how something as simple as a curve can mean the difference between safety and catastrophe. The story begins in the early days of jet airliner travel in the 1950s. Before jets, most airliners had piston engines and flew at relatively low altitudes. The cabins were not pressurized to the same degree, because the planes did not fly high enough to need it. But jet engines allowed planes to fly higher, above 30,000 feet, where the air is thin and offers less resistance, which saves fuel. At those altitudes, the air outside the plane is too thin for people to breathe, and the pressure is far too low for the human body to function. So the cabin has to be pressurized. The air inside is pumped up to a pressure similar to what you would feel at around 6,000 or 8,000 feet, while the air outside remains at the pressure of the high atmosphere. The difference between the inside pressure and the outside pressure is significant. The fuselage, the skin of the airplane, is stretched and pushed outward by the pressurized air inside, like a balloon being inflated. Every time the plane takes off, the cabin is pressurized. Every time it lands, the pressure is released. The fuselage expands and contracts, over and over, flight after flight. One of the first commercial jet airliners was the de Havilland Comet, a British design that entered service in the early 1950s. It was a beautiful airplane, sleek and modern, with 4 jet engines built into the wings. It had square windows. This seemed like a natural choice at the time. Buildings have square windows, cars have square windows. Why would an airplane be any different? The Comet flew successfully for a couple of years, and it seemed to herald a new era of fast, high-altitude travel. But then, in 1954, 2 comets broke apart in mid-air, with the loss of everyone on board. The accidents were deeply shocking, and the entire Comet fleet was grounded, while investigators tried to figure out what had gone wrong. The investigation was exhaustive. Engineers recovered wreckage from the sea, reconstructed the fuselages, and tested a full Comet fuselage in a water tank, repeatedly pressurizing and depressurizing it to simulate the stress of many flights. What they found was something they had not fully understood before. The square windows were the starting point for the failure. At each corner of each window, the sharp 90-degree angle concentrated the stress. The pressurization cycle pulled and pushed on the metal skin, and at the corners, the stress was magnified several times over. Tiny cracks began to form at these corners, so small that no one had noticed them during routine inspections. But over many pressurization cycles, the cracks grew. The metal was becoming fatigued, a word that means tired, in the same way a person gets tired, losing its strength after being flexed too many times. Eventually, the cracks reached a critical length, and the skin of the airplane tore open in flight, leading to explosive decompression and structural failure. This was a hard lesson, and it was learned in the hardest way possible. But it was learned thoroughly. The engineers who studied the comet's failures established the field of metal fatigue analysis as a formal discipline. They developed new methods for testing materials under repeated stress, and they redesigned the airplane windows. The square corners were eliminated. Future airliners, including later versions of the Comet and every commercial jet since, have windows with rounded corners or fully oval shapes that allow the stress to flow smoothly around the opening instead of concentrating at a sharp point. This principle is called stress concentration, and it applies to more than just airplane windows. A sharp corner in any material under repeated stress will attract cracks. A curve will distribute the stress more evenly, letting it flow around the opening like water around a smooth stone. The round window is now one of those small, quiet features of modern life that no one really thinks about. When you board an airplane, you walk past rows of oval windows, and they look right. They look finished. They look like they belong. The square windows of the early Comet, in retrospect, look odd, almost primitive. But the change was not cosmetic. It was a fundamental rethinking of how materials behave under repeated loading. The engineers of the 1950s were not foolish. They were working at the edge of what was known. Metal fatigue was not a new concept, but it was not as thoroughly understood as it is today. The Comet accidents pushed the entire field forward, and the round window became one of the visible legacies of that painful but necessary education. Stress concentration is a fairly simple idea once you picture it. Imagine a flat sheet of metal with a hole cut in it. If the hole is round, the stress flows around it evenly, like a river flowing around a round island. The stress is slightly higher at the edges of the hole than it is in the rest of the sheet, but not dramatically so. Now imagine a square hole in the same sheet. At the corners, the stress lines bunch up, like water trying to squeeze around a sharp bend. The stress at the corner can be many times higher than the average stress in the sheet. That is where the crack will start. That is where the material will first begin to tear. The solution is not to make the metal thicker everywhere, because that would add weight and cost. The solution is to remove the sharp corners, to round them off, to give the stress a smooth path to follow. The oval airplane window is the direct result of that insight. The round window also has another, more subtle benefit. The window on an airliner is actually multiple layers of acrylic or glass, with an air gap between them. The inner pane you can touch is not structural. It is there mainly for insulation and to protect the structural panes from scratches. The outer and middle panes bear the pressure load, and because they are round or oval, the pressure load is distributed evenly around the entire perimeter. There is no corner that carries a disproportionate share of the force. The window sits in its frame like a calm eye, letting the stress of the fuselage flow past it without getting tangled. There is something restful about a round shape. It does not catch. It does not snag. It lets the eye and the mind move around it without stopping. A sharp corner demands attention. A curve does not. This is true in visual design, but it is also true in structural design. A curve lets the force keep moving. A corner forces the force to change direction suddenly, and that sudden change is where the trouble begins. The round airplane window is a quiet demonstration of this principle, a shape that is gentle to the material and gentle to the forces that flow through it. The de Havilland Comet was eventually redesigned and returned to service, but its reputation never fully recovered. Other aircraft manufacturers, particularly Boeing and Douglas in the United States, learned from the Comet's failures and incorporated the lessons into their own designs. The Boeing 707, which became the dominant jet airliner of the 1960s, had oval windows from the start. So did every airliner that followed. The round window became standard, not because of a regulation, exactly, but because the engineering case for it was overwhelming. No one would build a pressurized aircraft with square windows now. The knowledge is too well established. And that knowledge extends far beyond airplanes. Stress concentration is a consideration in the design of ships, bridges, pressure vessels, pipelines, and any other structure that must withstand repeated loading. Welders and machinists are trained to avoid sharp internal corners in their work, to grind them smooth, to use gradual curves instead of abrupt angles. The principle is embedded in building codes and manufacturing standards around the world. It is one of those fundamental lessons of material science that, once learned, seems almost obvious. But it was not obvious in the early 1950s. It had to be discovered, and the discovery came at a cost. Now, when you sit in an airplane, you can look at the window beside you and see the shape that came out of that hard-won understanding. The oval frame, the smooth curves, the multiple panes of clear material. The sun shines through it, or the runway lights, or the dark of the night sky. The window is holding back a pressure difference of several pounds per square inch, which adds up to hundreds of pounds of total force on each window. And it does so without complaint, without cracking, flight after flight, because the stress flows around it like a calm river around a smooth island. The roundness is the reason. There is a gentleness to this kind of engineering. It does not overpower the problem with brute force. It works with the nature of the material, understanding where it is weak and giving it a shape that protects those weak points. Metal does not like sharp corners. It tells you so, quietly, by cracking at them. The engineer's job is to listen and to design a shape that the metal can live with. The round window is a kind of agreement between the designer and the material, a compromise that lets both sides get what they need. The passengers need a view and light. The metal needs a smooth path for its stress. The oval shape gives both. And now, as you lie here in the dark, you might think about the sharp corners in your own life, the places where stress concentrates, a worry that keeps coming back to the same sharp edge, a task that feels like it has no smooth way forward, a memory that snags. The lesson of the round window is not that you can eliminate all stress. The pressurization cycle will still happen. The cabin will still expand and contract. But you can change the shape of the opening. You can round the corners. You can let the stress flow instead of catching. You can give your mind a smoother path so that the forces that move through it do not all gather at one sharp point. This is not a solution you have to work at. It is just a shape you can imagine, a gentle curve around whatever feels hard, a softening of the edges that lets the pressure pass through without doing damage. Somewhere in the sky, right now, an airplane is flying through the night. Its oval windows are dark, the passengers inside asleep or reading by dim overhead lights. The fuselage is pressurized, the metal skins stretched taut. The stress is flowing around each window in a smooth, even ring, distributed by the careful shape of the frame. The cracks that might have started at sharp corners are not starting, because there are no sharp corners. The airplane is safe, the night is calm, the windows are round, and the forces are at peace. And you are here, on the ground, in the quiet, letting your own stresses flow around whatever smooth shapes you can imagine, softening into the dark, softening into sleep. We have moved through large structures and small windows, through bridges and dams and the smooth oval frames that hold the sky at bay. Now we are going to turn to something much more mechanical, something you can feel with your hands and your feet. Gears. Gears are everywhere in the built world. They are inside the engine of a car, inside the watch on your wrist, inside the blender on the kitchen counter, inside the elevator we thought about earlier. They are so common that they can seem almost invisible, just another part of the background machinery of daily life. But the way they work is a quiet, elegant trade-off, a swap of one thing for another, and understanding that trade-off opens up a whole way of thinking about how machines do what they do. A gear is, at its simplest, a wheel with teeth. The teeth are cut into the edge of the wheel at regular intervals, and they are shaped so that they can fit into the teeth of another gear. When two gears are meshed together, Turning one forces the other to turn as well. The teeth interlock, and the motion of the first wheel is transferred to the second wheel without slipping. This is the basic function of gears, to transfer turning motion from one shaft to another. But gears do more than just transfer motion. They also change it. They can make a turning motion faster or slower, and they can make it weaker or stronger. And they always do these two things together, in opposite directions. That is the trade-off. Imagine two gears, one small and one large, with their teeth meshed. The small gear has, let us say, 10 teeth. The large gear has 20 teeth, twice as many. When you turn the small gear one full rotation, all 10 of its teeth pass through the mesh point. Because the teeth are locked together, those 10 teeth will pull along 10 teeth of the large gear. But the large gear has 20 teeth in total, so 10 teeth is only half of its full circle. The large gear will turn only half a rotation. If you want the large gear to turn one full rotation, you have to turn the small gear twice, so the small gear spins fast, and the large gear spins slow. This is the first half of the trade-off. Speed is reduced, but something else happens at the same time. When you turn the small gear, you are applying a certain amount of twisting force to its shaft. That twisting force is called torque. When the small gear pulls on the large gear, the torque is transferred through the teeth. But because the large gear is bigger, the same force at the teeth has more leverage on the large gear's shaft. The torque on the large gear is greater than the torque you applied to the small gear. In this example, with a 10-tooth gear driving a 20-tooth gear, the torque is doubled. You get twice the twisting force, but at half the speed. This is the second half of the trade-off. Force is increased. The reverse is also true. If you turn the large gear as the driver and the small gear as the follower, then the small gear will spin faster than the large one. With a 20-tooth gear driving a 10-tooth gear, one turn of the large gear produces 2 turns of the small gear. The speed is doubled, but the torque is halved. You get more speed, but less force. This is the trade-off in the other direction. This trade-off between speed and force is called mechanical advantage. The word advantage does not mean you are getting something for free. You are not. The total amount of energy stays the same, minus a little loss to friction. What you are doing is trading one kind of benefit for another. You can have more force but less speed, or more speed but less force. You cannot have both at the same time from the same set of gears. The gears force you to choose, and the choice depends on what you need the machine to do. The best way to feel this trade-off directly is to think about a bicycle. A bicycle has gears, a set of them on the front near the pedals and a set on the back near the rear wheel, connected by a chain. The chain is just a way of linking two gears that are far apart, but the principle is exactly the same as two gears meshed directly together. When you shift gears on a bicycle, you are changing the size relationship between the front gear and the back gear. When you are climbing a steep hill, you shift into a low gear. This means you are using a small front gear and a large back gear. The pedals turn many times for each rotation of the rear wheel. You are trading speed for force. Your legs spin quickly, but each push on the pedal delivers a strong twisting force to the wheel, enough to pull you up the hill. It feels light on your legs, but you have to pedal fast to make any progress. You are choosing force over speed. When you are on a flat road and want to go fast, you shift into a high gear. This means you are using a large front gear and a small back gear. Each rotation of the pedals turns the rear wheel many times. You are trading force for speed. Your legs push harder, more slowly, and the bicycle shoots forward. It feels heavy on your legs, but you cover a lot of ground with each pedal stroke. You are choosing speed over force. The bicycle lets you feel this trade-off in your muscles. On the hill, your legs move fast, but the resistance is light. On the flat, your legs move slow, but the resistance is heavy. The gears are not giving you more energy. They are just letting you match your body's output to the demands of the terrain. The same principle applies to a car's transmission, where gears let the engine operate in its most efficient speed range, while the wheels turn at whatever speed the road requires. It applies to a hand-cranked winch, where a small gear turning a large one lets you lift a heavy load with a modest pull on the crank, though you have to crank many times to raise the load a short distance. It applies to a clock, where a series of gears steps down the fast unwinding of a spring into the slow, steady motion of the hour and minute hands. Gears are ancient technology. The basic idea of a toothed wheel has been around for more than 2,000 years. The Antikythera mechanism, an astronomical calculating device built by the ancient Greeks and recovered from a shipwreck, used dozens of precisely cut bronze gears to model the movements of the sun and moon and planets. The gears in that device are not so different in principle from the gears in a modern transmission. They transfer motion and they change the relationship between speed and force. The materials have improved, the manufacturing precision has increased enormously, but the underlying geometry is the same. A tooth is a tooth, a mesh is a mesh. The trade-off is eternal. There are many different kinds of gears, each with its own shape and purpose. Spur gears are the simplest, straight teeth cut parallel to the shaft, and they are what most people picture when they think of a gear. Helical gears have teeth cut at an angle, so that the contact between teeth is gradual and quiet, which is why they are often used in car transmissions. Bevel gears are cone-shaped and let you change the direction of rotation, transferring motion around a corner. Worm gears use a screw-like gear that turns a toothed wheel, allowing very large reductions in speed in a small space, and they have the special property that the worm can turn the wheel, but the wheel cannot turn the worm, which makes them useful for lifting mechanisms that must not backdrive. Rack and pinion gears turn rotary motion into linear motion, as in the steering of a car. But all of these variations share the same fundamental trait: speed for force, force for speed, never both. The simplicity of gears is part of what makes them so satisfying to think about. There is no mystery. The teeth go in, the teeth go out. The numbers add up. If you know how many teeth each gear has, you know exactly how the speed and force will change. It is a rare corner of the physical world where the outcome is perfectly predictable, where the trade-off is laid out in advance with nothing hidden. Gears do not deceive. They do not promise more than they can deliver. They just sit there, meshed together, waiting to be turned, ready to do their quiet work of swapping one kind of effort for another. And there is something soothing about that, especially at night, when the mind is trying to shift out of the high gear of the day into the low gear of sleep. You have been spinning fast all day, your thoughts turning quickly, your energy output high, but the torque perhaps low, a lot of motion without a lot of forward progress. Now it is time to shift. You can feel the gears changing, the mental derailleur moving the chain to a different combination. The front gear gets smaller. The back gear gets larger. The pedaling becomes lighter, the progress slows. That is all right. You are not trying to go fast anymore. You are climbing a gentle hill into the dark, and the low gear is the right gear for that. Each breath is a slow turn of the pedals. Each exhale is a quiet click of the chain, settling onto the next tooth. The mechanical advantage is working in your favor now, trading away speed to gain the gentle, steady force that carries you upward into rest. The gears in the world around you are still now. The transmissions of parked cars are in neutral or park, their gear teeth not meshed, their shafts not turning. The gears in factory machines are stopped for the night, quiet under their housings, waiting for the morning shift. The gears in clocks are still turning, some of them, the ones in the old-fashioned wind-up clocks on mantelpieces and bedside tables, ticking softly as the escape wheel releases one tooth at a time, marking the slow passage of the dark hours. Even the digital clocks rely on gears somewhere in the power grid, turbines spinning, generators turning, the mechanical advantage of steam and wind and falling water converted into the alternating current that lights the numbers on the clock face. Some of them are always turning somewhere, keeping the world's quiet rhythm. And you can let that rhythm carry you now. The gears of your mind have shifted down as far as they can go. The pedals turn slowly. The force is gentle. The hill is not steep. The night is long, and there is no rush to reach the top. You can just keep pedaling, slow and steady, the chain humming softly, the gear teeth meshing perfectly, each thought a little slower than the last, each breath a little deeper, until the road levels out and the pedaling stops and you coast, silently, into sleep. We have talked about gears and the quiet trade-offs they make, trading speed for force and force for speed. Now we are going to shift to something even simpler, something you walk over every day without a second thought: a manhole cover. That heavy metal disc set into the street, the one that clanks when a car tire rolls over it, the one with the raised pattern on top. It is round. Have you ever stopped to wonder why? It seems like a small thing, almost too small to deserve an answer, but the answer, when you sit with it, is a small piece of perfect practical logic. A manhole cover is round for three main reasons, and each one is a quiet demonstration of how good design often means solving several problems at once with a single, simple choice. The first reason is the most elegant. A round cover cannot fall through its own opening. This is not true of most other shapes. Imagine a square cover, the kind you might see on a cardboard box. A square cover fits neatly onto a square hole when it is placed flat, aligned with the edges. But if you lift that square cover and tilt it, you can slip it through the hole diagonally. The diagonal of a square is longer than its side, so there is a way for the cover to pass through the opening it is supposed to close. If a worker in a manhole were underneath, and a square cover were dropped or knocked loose, it could fall through the hole and cause serious injury. The same is true of a rectangular cover, or an oval cover, or a triangular cover. Almost any shape with straight edges and corners can be maneuvered through its own opening if tilted the right way. A circle is different. The width of a circle is the same in every direction. The diameter, the distance from one edge through the center to the opposite edge, is constant. There is no diagonal that is longer than the diameter, so no matter how you tilt a round manhole cover, you cannot pass it through a round hole that is just slightly smaller than the cover itself. The cover will always bind against the rim before it can slip through. It will always be wider, in whatever direction you try to push it, than the hole it is meant to close. This is a simple geometric fact, and it makes the round cover the safest shape for the job. A worker below ground is protected from the one hazard that every other shape would leave open, the hazard of the cover itself becoming a falling object. The second reason is related to the first, but from the worker's point of view at the surface. A round cover is easier to move. These covers are heavy. A typical cast iron manhole cover can weigh anywhere from 100 to 300 pounds, depending on its size and the traffic load it is designed to bear. Moving a weight like that across a street is hard work, but a round cover can be rolled. If you tip it up on its edge, it becomes a wheel, and you can roll it along the ground rather than having to lift and carry it. No other common shape does this as easily. A square cover would have to be lifted and walked, or dragged, or flipped end over end. A round cover rolls smoothly, with a steady, predictable motion, and it only needs to be lifted when it is time to set it back in place. This saves effort and reduces the chance of a worker straining or dropping the cover. The third reason is about alignment. A round cover fits its hole in any rotation. There is no right way up, no corners to match, no orientation to check. A worker removing a round cover can set it aside and then, when it is time to replace it, simply roll it back and drop it in. It will seat perfectly every time, no matter how it is turned. A square cover would require the worker to align the corners, which might mean turning the cover in the dark, in the rain, in the middle of traffic, until it lines up. A triangular cover would be even worse. The circle eliminates all of that. It is the shape of least effort, the shape that asks nothing of the person handling it except that they put it back where it belongs. These three reasons, safety from falling through, ease of rolling, and universal alignment, together make the circle the near-universal choice for manhole covers around the world. There are exceptions. Some older cities have rectangular covers or covers of other shapes, often for historical reasons or because the opening leads to a space that is not a vertical shaft. But the vast majority of the covers you see in the street, the ones you walk over and drive over without thinking, are round. And the reasons they are round are not arbitrary. They are the result of a quiet kind of problem solving, the kind that engineers do when they are thinking about how a thing will actually be used, day after day, by real people in real conditions. There is another, more subtle benefit to the round shape, one that has to do with how the cover sits in its frame. The frame, the metal ring that is set into the pavement, has a lip that the cover rests on. Because both the cover and the lip are round, the weight of the cover and any traffic above it is distributed evenly around the entire circumference. There are no corners where stress might concentrate, the way it concentrates at the corners of a square window. The round cover settles into its frame like a stone dropping into a pond, with the force spreading outward equally in all directions. This helps the cover resist cracking or deforming over time, even under the heavy, repeated pounding of cars and trucks. The manhole cover is one of those objects that hides its cleverness so completely that it is easy to dismiss it as just a piece of metal. But think about what it does. It seals an opening that leads down into a hidden world, a world of pipes and cables and tunnels, the veins and arteries of the city. It keeps that opening safe for pedestrians and vehicles above. It keeps people and animals from falling in. It withstands the weight of passing traffic, the heat of the summer sun, the freeze of winter ice, the corrosive effects of road salt and rain. It does all of this for decades without complaining, without needing maintenance, without drawing any attention to itself. And it is removed and replaced by workers who need to access the underground world quickly, safely, and with the least possible trouble. The round shape makes every part of that process easier. The raised pattern on the top of the cover is not just for decoration either. It provides traction for tires and shoes, so that the metal is not slippery when wet. It also adds stiffness to the cover, allowing it to be slightly thinner and lighter than a flat disc would be, because the raised ribs act like small beams, resisting bending. The pattern is often a grid or a series of concentric circles or a waffle-like texture, and it is designed to channel water off the surface so that puddles do not form. All of this is thought through, tested and standardized, so that the manhole cover you see on your street is the result of decades of incremental improvement, each small change making it a little better at its job. And yet, for all that thought, the manhole cover is almost invisible. You walk over it. You drive over it, you hear it clank. You might glance down and see the pattern, the name of the utility company or the city cast into the iron, but you do not stop and wonder about it. It is part of the background texture of the street, as unremarkable as the asphalt itself. That is a kind of success. The best design is the design that does its job so well that it disappears. The round manhole cover has achieved that. It is a perfect, quiet solution to a set of problems that most people will never know existed. And there is something pleasing about a puzzle with such a clean answer. Why are manhole covers round? Because a circle is the only shape that cannot fall through its own opening. Because a circle is easy to roll. Because a circle fits in any orientation. 3 answers, each one satisfying on its own, and together they make the choice feel inevitable, as if no other shape was ever really a contender. The circle is the shape of safety, the shape of efficiency, the shape of least resistance. It is the same shape as the sun and the moon, the same shape as a ripple spreading on a pond, the same shape as the round window on the airplane we thought about earlier. Circles keep appearing in the built world wherever stress needs to be distributed, wherever alignment needs to be foolproof, wherever something heavy needs to be moved without lifting. Now, as you lie here, you might think about the manhole covers on the street outside, or on the street you grew up on, or on some street you crossed today without noticing. They are out there in the dark, cool and heavy, resting in their frames. The city is quiet above them. Below them, in the dark of the utility tunnels, water flows through pipes, electricity hums through cables, Data travels through fiber optic lines. The covers seal that hidden world off from the world above, keeping everything in its place. They are round, they are secure. They cannot fall through. They have been there for years, and they will be there for years more, doing their job without thanks, without notice, without a single moment of recognition from the feet and tires that pass over them. And you, in your own quiet way, are round too. Not physically, but in the sense of being complete, of being sealed, of having no sharp corners that might catch on the night. The thoughts that might have troubled you earlier are settling now, finding their own level, like a cover dropping into its frame. There is nothing that can fall through. There is nothing that needs to be aligned. You are safe. You are heavy with tiredness. You are resting in the frame of your bed, in the frame of this moment, and the weight of you is distributed evenly, pressing down without strain, held by the simple, perfect geometry of stillness. We have come a long way together through the quiet night. We have looked at bridges and buildings, at dams and airplane windows, at gears and manhole covers. Now we are going to finish our slow tour of hidden cleverness with something you have felt directly, something that touches your body every time you ride in a car. The way a car smooths out a bumpy road. You know the feeling. The car hits a pothole or a speed bump or a rough patch of pavement. You hear the thump. You feel a small jolt, a little lift and drop. But the jolt is muted, softened, as if something caught the bump before it could reach you fully and said, "Not so hard, not so fast. Let me take care of this." That something is the suspension system, and it is one of the most satisfying examples of quiet engineering at work. It takes a sharp, sudden shock and turns it into a gentle, rolling motion that fades away almost as soon as it begins. The suspension system in a car is made of two main parts. The first part is the spring. The second part is the damper, which is more commonly called the shock absorber. The spring and the damper work together, as a pair, and each one does a different job. The spring catches the bump. The damper catches the bounce. Without the spring, every bump would hit the car body directly, rattling your bones. Without the damper, the spring would just keep bouncing, up and down, long after the bump was gone. Together, they let the wheel dance over the rough road while you and the passenger cabin stay comparatively still. Let us start with the spring. A spring is a piece of metal, usually steel, that is shaped so that it can compress and stretch. The most common type in modern cars is the coil spring, which looks like a heavy metal spiral, the kind of spring you might picture on a pogo stick or a ballpoint pen, only much larger and stronger. Some cars use leaf springs, which are long, flat strips of metal stacked together. Some use torsion bars, which twist instead of compressing. But the principle is the same in every case. When the wheel hits a bump, the bump pushes the wheel upward. That upward push compresses the spring. The spring absorbs the energy of the bump by squeezing together. The metal coils get closer to each other, storing the energy temporarily in the form of elastic deformation, which just means the metal bends without breaking and wants to return to its original shape. If the car had only a spring and no damper, the spring would release that stored energy immediately after the bump. It would push the wheel back down, and the wheel would bounce off the road, and then the spring would compress again, and the wheel would bounce again, and this bouncing would continue for many cycles before friction slowly brought it to a stop. You would feel the car float and bob after every bump, like a small boat on a choppy sea. This would be uncomfortable and also dangerous, because a bouncing wheel is a wheel that is not firmly in contact with the road, and a car with wheels not firmly in contact with the road cannot steer or brake properly. That is where the damper comes in. The damper, or shock absorber, is a device that resists motion. It is usually a metal tube filled with hydraulic fluid, which is just a special kind of oil. Inside the tube, a piston moves up and down as the wheel moves. The piston has small holes or valves in it, and the fluid is forced to flow through these holes as the piston moves. Forcing a thick fluid through small holes takes energy. The fluid resists, Not because it is sticky in the way glue is sticky, but because it cannot move through the holes fast enough to allow sudden motion. The energy that the spring stored from the bump is converted into heat in the fluid, a tiny amount of warmth that dissipates into the air. The damper absorbs the bounce the way a soft pillow absorbs a fall, by turning motion into heat. The damper is tuned so that it allows the spring to compress on the first hit, absorbing the bump, but then it slows down the rebound, preventing the spring from just snapping back. The result is that the wheel moves up over the bump, the spring compresses, the damper resists the return motion, and within one or two small oscillations, the wheel is back to its normal position, rolling smoothly. The bump happened, the wheel felt it, the spring caught it, the damper calmed it. And you in the cabin felt only a slight rise and fall, a gentle reminder that the road is not perfectly flat, but not a jarring shock. The spring and the damper are a perfect example of two systems working together, each doing what the other cannot. The spring is good at storing energy and giving it back. The damper is good at dissipating energy, turning it into something harmless and letting it go. The spring provides the bounce, the damper provides the calm. Together they create a ride that is neither too hard nor too floaty, a compromise between comfort and control that engineers have been refining for more than a century. This same spring and damper combination appears in many places beyond cars. The tuned mass damper in the skyscraper we talked about earlier is a kind of shock absorber for buildings, damping out the sway with a heavy weight and hydraulic pistons. The suspension on a mountain bike uses springs and dampers to handle rough trails. Even the human body has its own version. The arches of your feet and the cartilage in your knees and spine act as springs, compressing to absorb the shock of each step. The muscles and tendons act as dampers, controlling the rebound and keeping your gait smooth. You can feel this when you jump off a low step. Your legs bend on landing, the springs compressing, and then your muscles control the return, preventing you from bouncing back up like a pogo stick. The body is an engineer too, and it arrived at the same solution long before cars existed. The springs and dampers in a car do not work alone. They are connected to a system of links and arms and bushings that allow the wheel to move up and down while keeping it aligned with the road. This system is called the suspension geometry, and its job is to make sure the tire stays flat on the pavement even as the body of the car leans and rolls. The geometry is designed so that when the car goes around a corner and the body leans outward, the wheels lean slightly inward, or outward, or stay upright, depending on what the engineers want for that particular car. It is a complex dance of angles and pivots, but the basic idea is always the same. Let the wheel move. Control the movement. Keep the tire on the road. At night, when the cars are parked and the roads are quiet, the springs and dampers are at rest. The springs are slightly compressed by the weight of the car body pressing down on them, but they are not moving. The dampers are cool, their fluid still, their pistons motionless. They have spent the day absorbing the jolts and shimmies of the road, and now they are resting, like everything else in the quiet dark. Tomorrow they will go back to work, compressing and rebounding, resisting and calming, doing their invisible job under the wheel wells of every car on the road. There is a deep physical comfort in the way a car's suspension works, because it is a kind of gentleness made out of metal and oil. It does not fight the road. It does not try to keep the car perfectly rigid and unmoving. It lets the road be what it is, rough and uneven and full of small surprises, and it absorbs those surprises one by one, cushioning them, softening them, turning sharp shocks into slow waves. The suspension is a lesson in how to handle the bumps of a journey. You do not have to resist every jolt with stiff determination. You can let the springs of your attention compress, absorbing the impact, and then let the dampers of your breath slow the rebound, bringing you back to center without bouncing, without rattling, without carrying the shock any further than it needs to go. Now, as you lie here, you can feel the mattress under you doing its own quiet version of what a car's suspension does. The mattress is a spring, compressing under your weight, conforming to the shape of your body. The foam and fabric are dampers, resisting sudden motion, turning your small shifts and turns into gentle, slow settlements. You sink in, the mattress holds you, the tiny movements of your breathing are absorbed and calmed. You are the passenger in a cabin that is parked for the night, the road behind you, the journey over, the springs resting, the dampers cool, the whole system still. And the bumps of the day, whatever they were, have been handled. The springs caught them, the dampers calmed them. They are just tiny amounts of heat now, dissipated into the dark, gone. The road ahead is smooth and straight, and you are not even driving. You are just riding, quietly, in the back seat of your own tired body, letting the suspension do its work, letting the miles of the night pass under your wheels without a sound, without a jolt, without anything but this slow, soft, steady drift towards sleep. The road is smooth now. The bumps are behind you. The springs have done their work. The dampers have quieted the last bounce, and the car of your thoughts is coasting on a long, straight, gentle road through the dark. There is no need to steer. There is no need to watch the road ahead. You can just sit back, or lie back, and let the miles pass under you without counting them. We have traveled together through a landscape of ordinary things, bridges and wings and towers and elevators and roads and dams and windows and gears and covers and springs. And all of them, in their own quiet ways, have been doing the same thing, holding balance, managing forces, trading one thing for another, leaving room for movement, letting stress flow around smooth curves, catching jolts and calming aftershocks. The tall building still sways somewhere in the night, a slow, barely perceptible lean into the wind and then back again. The steel sphere inside it, the tuned mass damper, swings in its own quiet rhythm opposite to the building's motion, a dance partner that never tires. The building does not fight the wind. It moves with it, just a little, just enough to let the force pass through without breaking anything. That is a way of being in the world. Not rigid, not resistant, but flexible in a controlled way, strong enough to bend and return. The round manhole cover rests in its frame on some dark street. It cannot fall through. That is the simple, perfect fact of it. No matter how you tilt it, it will not slip through its own opening. It is safe. It is secure. It fits in any rotation, asking nothing of the worker who set it there, except that it be placed back where it belongs. The cars have stopped running over it for the night. The street is quiet above it. Below, in the dark of the utility tunnels, the water moves slowly through the pipes. The electricity hums softly. The city's hidden life goes on. The cover seals it all in, a quiet lid on a hidden world, round and heavy and still. The curved road is dry now, after the rain. The camber did its work, tilting the water off to the sides, guiding it into the gutters and the drains. The road looks flat, but it is not. It is shaped, carefully, to let the water go where it needs to go. That gentle curve is still there in the dark, invisible under the streetlights, waiting for the next rain, waiting to do its quiet job again without thanks, without notice. The road is empty. The painted lines are pale in the darkness. The surface is smooth and dry and ready for the morning. These images drift through the quiet of the room, through the quiet of your mind. The swaying building, the round cover, the curved road. They do not need to be explained again. They do not need to be remembered. They are just there, hanging in the dark like the faint after-image of a light that has been turned off. You can let them float. You can let them fade. There is no test at the end of this. There is no lesson you have to carry forward. The only thing that matters now is the slow, easy drift of your own breath, the soft weight of your body on the mattress, the growing distance between you and the day that is already slipping away behind you. All of the things we have thought about together are still out there, doing their work. The bridge is breathing, its expansion joints opening and closing by fractions of an inch as the night air cools the steel. The airplane is flying through the dark, its winglets calming the vortices, its oval windows holding the pressure of the cabin in a smooth, even ring of stress. The elevator is parked at the ground floor, its counterweight hanging near the top of the shaft, the balance between them perfect and still. The dam is holding back the lake, heavy and curved, letting the water press, and finding that pressure only locks it tighter into the canyon walls. The gears are stopped in their transmissions, their teeth not meshed, their shafts not turning. The springs are compressed under the weight of parked cars, the dampers cool, the fluid motionless. All of it is resting, all of it is balanced, all of it is exactly where it needs to be. And you are here, in the middle of it all, part of the same quiet system. Your body knows how to settle. Your breath knows how to find its rhythm. Your mind knows how to let go of thoughts the way a road lets go of rain, tilting them gently to the sides, letting them drain away into the dark. You do not have to hold on to anything. You do not have to keep yourself upright against the pull of the day. You can just lie here, heavy and still, like the dam holding back the lake, not fighting the pressure, but simply being present, being solid, being at rest. The sentences are getting shorter now. They are slowing down. There is less to say, and more space between the words. The rhythm of the voice is becoming like breath. In, out. A thought rises, and then it falls. A word hangs in the air, and then it dissolves. You are drifting now, not toward anything in particular, just drifting, the way a leaf drifts on still water, turning only because the water itself is turning underneath. The night is deep. The stars, if there are stars where you are wheeling slowly overhead, or the clouds are covering them, or the city lights are dimming them to a faint glow. The built world is quiet. The natural world is quiet. The boundary between them is soft, blurred by the dark, and you are resting right at that boundary, held by both, belonging to both. There is nothing more you need to do. There is nowhere else you need to be. The cleverness we have talked about, the hidden balance, the quiet forces, the simple trade-offs, they are not just in bridges and buildings and machines. They are in you. The way you breathe is a cycle of tension and release. The way you rest is a surrender to gravity, a trusting of the surface that holds you up. The way you let go of a thought is a kind of damping, a calming of the aftershock, a turning of mental energy into the quiet warmth of stillness. You can let go now, fully, completely. The voice will stay with you a little longer, but it is softening too, becoming less distinct, more like a murmur, more like a memory of a sound. The last images are fading. The swaying building settles into its foundation. The round cover seals the dark below. The curved road stretches out into the distance, empty and dry and waiting. The night holds you. The balance holds. The forces that have carried you through this long, slow journey are still there, but they do not need your attention. They will keep doing their work whether you are watching or not. The bridge will keep breathing. The winglet will keep calming the air. The dam will keep resisting the lake. The spring will stay compressed. The damper will stay cool. The gear teeth will stay still. And you will sleep. You are already almost there. The road is ending. Or maybe it is not ending, but turning into something else, a path that does not need to be followed, a landscape that does not need to be seen. You are crossing a bridge now, a bridge with no gaps, no cables, no towers, just a smooth passage from waking to rest. The other side is close. The other side is here. The voice is very quiet now. The words are very few. The space between them is very wide. You can step into that space. You can let it close around you. You can let the quiet be complete.